There is something in the universe that should not be there. A structure so vast it stretches across 10 billion light-years of space. To put that in perspective, if you could travel at the speed of light, it would take you 10 billion years just to cross from one end to the other. The Hercules-Corona Borealis Great Wall is not just large, it is impossible. According to the cosmological principle, the bedrock assumption that underlies every model of how the universe is built, nothing larger than 1.2 billion light-years should exist. The math does not allow it, the physics forbids it, and yet there it sits, nearly 10 times too large, embedded in the deep sky like a fact that refuses to behave. This is not a fringe claim. It is not a measurement error or a trick of perspective. It is a pattern of gamma-ray bursts clustered across a region of space so enormous that it challenges the very framework we use to understand reality. And it is not alone. Out there, scattered across the observable universe, are objects and structures that defy every intuitive sense of scale we carry. Black holes, with the mass of 66 billion suns. Galaxies spanning 4 million light-years, containing 100 trillion stars. Superclusters that stretch across 500 million light-years, binding tens of thousands of galaxies into a single gravitational flow. Each one pushes the boundary of what we thought was possible. Each one forces us to ask uncomfortable questions about the rules we assumed were universal. So how does the universe build something 10 billion light-years long? How do structures this large even form in a cosmos that is only 13.8 billion years old? And what does it mean for our understanding of space, time, and the fabric of existence itself when the largest thing we have ever found is something our best theories say cannot exist? This is that story. Welcome to Space Dust. If you're new here, please subscribe. We make these documentaries every day and we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in for a great journey. We live on a rock. That rock is a little under 13,000 kilometers wide. Most of us will never travel more than a few thousand kilometers from the place we were born. The farthest any human being has ever physically gone is the moon, roughly 380,000 kilometers away. 12 people have stood on its surface. The last one left in 1972. That's it. That's the full scope of human exploration measured in actual footsteps. 380,000 kilometers. It seemed like an impossible distance at the time. It still does if you're honest about it. Now, let me tell you about something else. There is a structure in the universe that is 10 billion light-years long. Not 10 billion kilometers, 10 billion light-years. A light-year is the distance light travels in 1 year. Light moves at just under 300,000 kilometers per second. In 1 second, a beam of light could circle the Earth 7.5 times. In 1 year, that same beam travels about 9.5 trillion kilometers. And this structure, this thing hanging in the cosmos like a scar across the skin of reality, is 10 billion of those years wide. If you fired a beam of light from one end of this object, it would take 10 billion years to reach the other side. The universe itself is only about 13.8 billion years old, meaning a photon that began its journey at one edge of this structure shortly after the Big Bang would only just now be approaching the other end. Assuming, of course, that the structure was already fully formed back then, which it probably wasn't, but that's a complication we'll get to later. For now, just sit with that number, 10 billion light-years. The human brain was not built to process distances like that. It wasn't built to process distances beyond maybe a day's walk. Everything else is abstraction. We can write the numbers down. We can do the math. We can nod along and pretend we understand, but we don't. Not really. Not in any way that connects to the lived experience of being a thing with a body that moves through space. You know how far 10 billion light-years is? I don't either. Nobody does. The best we can do is stack smaller, incomprehensible things on top of each other until the pile gets so high we give up and call it a day. Let's try anyway. Start with the Sun. It's about 150 million kilometers from Earth. We call that distance 1 astronomical unit. Pluto, at the far edge of the solar system, orbits at about 40 astronomical units. The Voyager 1 spacecraft, the most distant human-made object, is currently about 160 astronomical units away. It's been travelling since 1977 and it's barely scratched the surface of interstellar space. The nearest star to our Sun, Proxima Centauri, sits at about 4.2 light years. That's roughly 268,000 astronomical units. If you could somehow drive a car at highway speed toward Proxima Centauri without stopping, it would take you about 48 million years to get there. The Milky Way galaxy, our home galaxy, is about 100,000 light years across. It contains somewhere between 100 billion and 400 billion stars. If you wanted to count them at a rate of 1 per second, it would take you somewhere between 3,000 and 12,000 years just to finish counting, assuming you didn't sleep, or eat, or do anything else. The nearest large galaxy to ours, Andromeda, is about 2.5 million light years away. That's 25 Milky Ways laid end to end. And Andromeda is close by galactic standards. It's practically next door. The Observable Universe, the bubble of space from which light has had time to reach us since the Big Bang, is about 93 billion light years across. That number is bigger than 13.8 billion because space itself has been expanding the entire time the light was travelling. By the time a photon from the edge of the observable universe reaches Earth, the place it started has moved much farther away. Now take that 93 billion light-year sphere and remember that the Hercules-Corona Borealis Great Wall, the structure we're here to talk about, spans roughly 10 billion light years. That's about 1/9 of the entire observable universe. One single object, or at least one single claimed object, stretching across nearly 11% of everything we can see. If the observable universe were the size of Earth, the Great Wall would be a feature roughly the length of the Atlantic Ocean. Except oceans are things you can look at. You can stand on a beach and see water stretching to the horizon, and your brain accepts it because water is a thing you understand. The Great Wall is not a thing you can look at in any conventional sense. It exists at a distance so extreme that the light reaching our telescopes today left its source when the universe was less than a third of its current age. We're not looking at it. We're looking at where it used to be, billions of years ago, and trying to reconstruct what it might be now based on math and models, and a whole lot of assumptions about how space behaves when you're not watching. This is where things get uncomfortable, because the moment you start talking about structures 10 billion light years wide, you're not just talking about big things, you're talking about things that challenge the basic rules we thought governed how the universe is put together. There are principles in cosmology, assumptions baked so deeply into the models that for decades nobody bothered to question them. One of those principles is called the cosmological principle. It says that on the larger scales the universe should look roughly the same in every direction. Smooth, homogeneous, no giant walls stretching across 1/10 of the observable cosmos. The cosmological principle exists because without it the math breaks. If the universe is lumpy at the larger scales, if matter clumps together into structures so massive they violate the expected distribution, then something in our understanding of gravity, expansion, dark matter or dark energy is wrong. The Hercules-Corona Borealis Great Wall, if it's real, if it's actually a coherent structure and not just a statistical mirage, is exactly that kind of lump. A lump so large it shouldn't exist, and yet there it sits in the data, daring anyone to explain it. Before we go further, we need to talk about how we measure any of this. Because when you're dealing with distances that take billions of years for light to cross, you can't exactly pull out a tape measure. Astronomers use two main units for cosmic distances. The first is the light year, which we've already covered. It's a unit of distance, not time, even though the name makes it sound like time. 1 light year equals about 9.5 trillion kilometers, or if you prefer, about 63,000 astronomical units. The second unit is the parsec. 1 parsec equals about 3.26 light years, or roughly 31 trillion kilometers. The name comes from parallax arc second, a term rooted in an old technique for measuring nearby star distances by watching how they appear to shift against the background sky as Earth moves around the Sun. For distant objects, parsecs are often more convenient than light years because the math works out cleaner. You'll hear astronomers talk about kiloparsecs, thousands of parsecs, or megaparsecs, millions of parsecs. A megaparsec is about 3.26 million light years. The Hercules-Corona Borealis Great Wall is roughly 3 billion parsecs long, or 3,000 megaparsecs, depending on which estimate you trust. None of this makes the distance feel more real. It just gives us a vocabulary for pointing at things we can't actually see. Here's the thing about looking at the universe. The farther away you look, the farther back in time you see. Light takes time to travel. When you look at the Sun, you're seeing it as it was about 8 minutes ago. When you look at Proxima Centauri, you're seeing it as it was 4.2 years ago. When you look at Andromeda, you're seeing it as it was 2.5 million years ago, back when our ancestors were just figuring out how to chip rocks into tools. When astronomers look at the Hercules-Corona Borealis Great Wall, they're seeing light that left those galaxies roughly 10 billion years ago. The universe at that time was about 3.8 billion years old. Stars were younger, galaxies were still assembling. The Sun didn't exist yet, Earth didn't exist yet. Nothing you would recognize as familiar had happened. And in that ancient universe, somehow a structure 10 billion light-years long had already begun to take shape. That timeline is part of what makes the whole thing so strange. Structures that large should take an enormous amount of time to form. Gravity works slowly at cosmic scales. Dark matter pulls regular matter into clumps. Those clumps grow into galaxies. Galaxies collect into groups. Groups merge into clusters. Clusters link together along filaments of dark matter into superclusters and beyond. It's a process that unfolds over billions of years, layer by layer, like sediment building up on the ocean floor. For a structure the size of the Great Wall to exist when the universe was less than 4 billion years old suggests that something about that process happened much faster than the models predict, or that the initial conditions after the Big Bang were lumpier than we thought, or that our entire understanding of how large-scale structure forms is missing a piece. None of those options are comforting. Let's talk about what we mean when we say structure, because when you hear the phrase 10 billion light-years long, you might picture a solid object. A wall, as the name suggests. Something you could touch if you got close enough, assuming you could survive the trip. That's not what this is. The Great Wall is a filament, a chain of galaxy clusters and superclusters linked together by gravity and the cosmic web of dark matter that underlies everything. If you could somehow see it from the outside, it would look less like a wall and more like a loosely connected string of light stretching across the void. Each light is a cluster of galaxies. Each galaxy contains billions of stars. Each star is a sun, potentially surrounded by planets, moons, asteroids, comets, and all the rest. The space between those clusters is not empty. It's filled with gas, dust, stray stars, rogue planets, dark matter, and the faint glow of the cosmic microwave background. But compared to the dense knots of matter inside the clusters, the space between is close enough to nothing that we treat it as such. So when we say the structure is 10 billion light-years long, what we mean is that the galaxy clusters associated with it are distributed across a region of space that measures 10 billion light-years from end to end. It's not a single object in the way a planet or a star is a single object, it's a pattern. A shape drawn in galaxies across a canvas of space-time so large that the human mind has no frame of reference for it. You might be wondering how anyone even found this thing. It's not like you can point a telescope at the sky and see a line of galaxies stretching across a tenth of the universe. The discovery was far stranger than that. In the early 2010s, astronomers were studying gamma-ray bursts. These are the brightest explosions in the universe, short-lived flashes of high-energy light that occur when massive stars collapse into black holes or when neutron stars collide. Each burst lasts anywhere from a few milliseconds to several minutes, and during that time the explosion can outshine every star in its host galaxy combined. Gamma-ray bursts are useful as cosmic signposts because they're visible across enormous distances. If you want to map the large-scale structure of the universe, gamma-ray bursts give you a way to sample galaxies that are too faint or too far away to study any other way. A team of astronomers led by researchers in Hungary and the United States started plotting the positions of gamma-ray bursts on a map of the sky. They were looking for patterns, clusters, anything that might reveal how matter was distributed in the distant universe. They found a cluster, a tight grouping of gamma-ray bursts concentrated in a patch of sky near the constellations Hercules and Corona Borealis. 14 bursts out of 31 studied were packed into a region that shouldn't have had that many. The odds of it being random were something like 1 in several million. When they calculated the distances to those bursts, they found that the galaxies hosting them were all at roughly the same distance from Earth, about 10 billion light-years away. And when they mapped out the full extent of the structure those galaxies might belong to, the result was staggering. A filament stretching 10 billion light-years in length, 7.2 billion light-years in width, and nearly 1 billion light-years in thickness. They named it the Hercules-Corona Borealis Great Wall. The announcement was met with skepticism. Some astronomers questioned whether the gamma-ray bursts were actually tracing a real structure or just reflecting a statistical fluke. Others pointed out that gamma-ray bursts are rare and unevenly distributed, making them a shaky foundation for mapping large-scale structure. The distances involved were so extreme that small errors in measurement could make a huge difference in the calculated size. A few years later, some analyses suggested the structure might be even larger, possibly as much as 15 billion light-years across, though those estimates remain controversial. Other studies have argued that the clustering could be explained by the natural lumpiness of the universe without requiring a single coherent object. As of now, the Hercules-Corona Borealis Great Wall remains what scientists call putative. Possible? Claimed? Not proven? The data points towards something, but whether that something is a real structure or an artifact of how we're interpreting incomplete information is still an open question, which makes it perfect for what we're doing here. Because whether or not the Great Wall is real in the way its discoverers claim, the fact that we're even having the conversation tells you something important about where we are as a species. We have built instruments sensitive enough to detect explosions 10 billion light-years away. We have mapped the positions of galaxies across distances so vast that the light reaching us left its source when the universe was a fraction of its current age. We have developed mathematical models sophisticated enough to predict how matter should be distributed across the entire observable cosmos, and we have found things in that cosmos that don't fit the models. That's not a failure. That's the edge of the map. That's the place where the drawings stop and someone has written, "Here be dragons." Human intuition is a tool shaped by evolution to solve problems at human scales. How far can I throw this rock? How fast can I run from that predator? How much food do I need to store for winter? It is not a tool designed to comprehend 10 billion light-years. It is not a tool designed to hold the idea of a universe 93 billion light-years wide, filled with trillions of galaxies, each containing billions of stars, spread across billions of years of cosmic time. And yet, here we are, trying. Every time we point a telescope at the sky and find something new, something larger or stranger or older than we expected, we're forced to update the mental model, to stretch the boundaries of what fits inside the box labelled universe. The problem is that the box keeps getting bigger, and every time it does, the things we thought we understood start to look smaller and more fragile. So what comes next? If you want to understand the Hercules-Corona Borealis Great Wall, if you want to grasp how something that large could exist and what it means for the universe we live in, you need to start smaller. You need to build the ladder one rung at a time. You need to understand black holes, the densest objects in existence, where gravity becomes so strong that space-time itself tears. You need to understand galaxies, islands of billions of stars held together by gravity and dark matter spinning through the void. You need to understand how galaxies cluster, how those clusters link into superclusters, and how superclusters trace the filaments of the cosmic web. You need to see the universe not as a collection of isolated objects, but as a connected structure, a web of matter and energy stretched across space-time, shaped by forces we're only beginning to map. And you need to ask the uncomfortable questions. If the universe can build something 10 billion light-years long, what else is out there that we haven't found yet? If the models that predicted a smooth, homogeneous cosmos are wrong, what does that mean for everything else we think we know? The answers, if we ever find them, are going to be strange. But first, we need to talk about the things that break reality at the smallest scales. The objects so dense, so extreme, that they warp space and time into shapes that shouldn't be possible. The Devourers of light. The points of no return. The places where the universe folds in on itself and refuses to let go. We need to talk about black holes. Before we can understand anything 10 billion light-years wide, we need to understand the smallest points of infinite density. The places where matter goes to die. The objects that sit at the centres of galaxies like anchors, pulling everything toward them, warping space so severely that the rules stop working. We need to talk about black holes, and we need to talk about the biggest one we've ever found. A black hole is what happens when you take a stupid amount of mass and crush it into a space so small that gravity wins permanently. Not just wins the argument, wins so completely that the concept of escape stops having meaning. Gravity at that scale doesn't pull, it tears. It bends space-time itself into a pit so steep that even light, the fastest thing in the universe, cannot climb back out. There are two main types. Stellar mass black holes form when massive stars, at least 8 times heavier than our Sun, burn through all their fuel and collapse. The outer layers explode in a supernova. The core implodes. If the core is heavy enough, nothing can stop the collapse. Electrons get crushed into protons, forming neutrons. Then even neutron pressure fails. What's left is a singularity, a point of infinite density wrapped in an event horizon, the boundary past which nothing ever returns. These stellar remnants typically weigh between 3 and a few dozen times the mass of the Sun. They're small, cosmically speaking, dangerous if you're nearby, irrelevant if you're not. Then there are supermassive black holes. These are the monsters. They sit at the centres of most large galaxies, including our own. Our Milky Way's central black hole, Sagittarius A star, weighs about 4 million solar masses. It sounds like a lot. It is a lot. But in the hierarchy of supermassive black holes, it's practically a lightweight. The largest confirmed supermassive black hole we've ever found is called TON 618. Depending on which study you trust, it weighs somewhere between 40 and 66 billion times the mass of our Sun. For a long time, the estimate that circulated was 66 billion. More recent revisions using different measurement techniques have pushed the number down closer to 40 billion. Either way, it is so far beyond anything we have a reference for that the distinction barely matters. 40 billion suns. Imagine our Sun. Now imagine 40 billion of them, not scattered across space but compressed into a single object, a single point of gravitational collapse so extreme that it has carved a hole in the universe itself. The event horizon of TON 618, the boundary beyond which even light cannot escape, has a radius of roughly 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. Pluto orbits at about 40 astronomical units. The edge of TON 618's event horizon sits more than 30 times farther out. Light itself would take roughly 2 weeks to cross from one side of that horizon to the other. 2 weeks at 300,000 kilometers per second just to traverse the surface of a hole in space. If you could replace our Sun with TON 618, the event horizon would swallow everything. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper belt, everything out to a distance that makes the solar system look like a rounding error. You could fit dozens of solar systems across the diameter of that black hole's event horizon and still have room left over. But here's the thing. A black hole is not a thing you can see. It doesn't glow. It doesn't shine. It is, by definition, a region where light goes in and never comes out. The event horizon is not a surface in the way a planet has a surface. It's a boundary in space-time, a point of no return. Cross it, and the universe behind you stops being a place you can ever go back to. Your future becomes the singularity at the centre. There are no other options. Firing a rocket won't help. Moving at the speed of light won't help. Once you're inside, every direction you can point leads inward. So if black holes are invisible, how do we know TON 618 exists? How do we know how much it weighs? The answer is that we don't look at the black hole. We look at what it's doing to everything around it. TON 618 is not just a black hole, it's a quasar. That word is short for quasi-stellar object, a term from the 1960s when astronomers first started finding these things and had no idea what they were looking at. They looked like stars, bright points of light, but their spectra were all wrong. They were too bright, too far away, and their light was redshifted in ways that suggested they were receding from us at enormous speeds. It took years to figure out what quasars actually were. They're not stars. They're the glowing cores of distant galaxies, powered by supermassive black holes in the process of feeding. When a black hole feeds, it doesn't just swallow matter quietly. Matter doesn't fall straight in. It spirals, orbits decay, gas clouds crash into each other, heat up, and form a disk around the black hole called an accretion disk. The friction in that disk heats the gas to millions of degrees. At those temperatures, the gas glows. Not invisible light, although there's plenty of that. It glows across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The brightest quasars, like TON 618, outshine entire galaxies. Not just outshine them by a little, outshine them by orders of magnitude. TON 618 is roughly 140 trillion times brighter than our Sun. If you took every star in the Milky Way, all 400 billion of them, and added up their light, TON 618 would still be thousands of times brighter. One object. One black hole surrounded by a disk of doomed gas, brighter than a galaxy. That level of luminosity comes from the accretion process. The black hole itself is dark, but the material spiraling toward it is the brightest thing in the universe. Every atom that crosses the event horizon releases a fraction of its mass as energy on the way down. It's one of the most efficient energy production mechanisms in physics. More efficient than nuclear fusion, more efficient than matter-antimatter annihilation in most scenarios. A feeding supermassive black hole is the universe's most violent engine, and we can see it from billions of light years away because of how much light it produces in the process of eating. TON 618 sits roughly 10.4 billion light-years from Earth. Some sources put it farther, closer to 18 billion light-years in terms of co-moving distance, accounting for how much space has expanded since the light left. Either way, the light we see today left that quasar when the universe was less than 4 billion years old. It has been travelling toward us for more than 10 billion years, crossing an expanding universe, threading through voids and filaments, passing galaxy clusters and dark matter halos, until finally it reached a small rocky planet orbiting an unremarkable star, where a species of primates built a telescope and pointed it at the right patch of sky. The fact that we can measure TON 618 at all is absurd. The fact that we can estimate its mass to within a factor of 2 is borderline miraculous. Here's how the mass measurement works. Black holes don't come with labels. You can't weigh them directly. What you can do is measure how fast the gas around them is moving. The faster the orbital speed, the stronger the gravitational pull and the more massive the black hole must be. Astronomers look at the spectrum of light coming from the quasar and search for broad emission lines, specific wavelengths of light emitted by hydrogen, carbon or other elements in the accretion disk and the surrounding clouds of gas. Those emission lines are Doppler shifted. Gas moving toward us appears slightly bluer. Gas moving away appears slightly redder. When you have a disk of gas orbiting a black hole at thousands of kilometers per second, the emission lines get smeared out, broadened by the range of velocities. Measure the width of those lines, apply some physics about orbital dynamics, and you can back out an estimate of the black hole's mass. Different elements give different results. Early estimates of TON 618's mass used hydrogen beta lines and came up with 66 billion solar masses. Later studies used carbon-4 lines and arrived at closer to 40 billion. The discrepancy comes from uncertainties in how the gas is distributed, how much of it is in the disk versus clouds farther out, and how much radiation pressure from the quasar is pushing the gas around. So when you hear that TON 618 weighs 66 billion solar masses, know that the number is not settled. It's an estimate, and estimates this extreme come with error bars the size of galaxies. But even at the lower end, 40 billion solar masses, TON 618 is still the most massive black hole we've confirmed. And the fact that it exists at all is a problem. Black holes grow in two ways. They eat and they merge. Eating is slow, merging is rare. The standard model of black hole growth starts with a stellar mass black hole, a few times the mass of the Sun, left behind after a supernova. That seed black hole sits at the centre of a forming galaxy, pulling in gas. Every time it swallows gas, it gains mass. Every time it gains mass, its gravity gets stronger, and it can pull in more gas. Feedback loop, but there's a limit. As the black hole feeds, the accretion disk heats up and starts radiating enormous amounts of energy. That energy pushes back against the infalling gas, creating radiation pressure. At a certain feeding rate, called the Eddington limit, the outward radiation pressure exactly balances the inward pull of gravity. Feed faster than that, and you blow away your own food supply. The black hole chokes. A black hole feeding at the Eddington limit doubles its mass every few tens of millions of years. Sounds fast, it's not. Start with a 10 solar mass black hole, let it feed continuously at the Eddington limit for 4 billion years, and you end up with a black hole weighing maybe a few 100 million solar masses. Not 40 billion, not even close. To get to 40 billion solar masses in less than 4 billion years, something has to break. Either the black hole started much heavier than a stellar remnant, or it fed much faster than the Eddington limit allows, or it grew through a series of rapid mergers with other black holes, each of which also had to grow impossibly fast. Astronomers have proposed several ideas. One is called direct collapse. In this scenario, giant clouds of primordial gas in the early universe collapse straight into black holes without forming stars first. If those seed black holes started at 100,000 solar masses or more, they'd have a massive head start. Grow from there and you can hit billions of solar masses in the available time. Another idea is super Eddington accretion. Maybe in the chaotic early universe, before galaxies had settled into their current structures, black holes could feed faster than the Eddington limit, because the gas around them was denser, colder, and less able to resist infall. Some simulations suggest this might work under specific conditions, but it requires a lot of fine-tuning. A third possibility is that primordial black holes, formed in the first moments after the Big Bang from density fluctuations in the hot plasma, served as seeds. These would have predated stars entirely, and could have started growing the instant the universe cooled enough for gas to clump. If primordial black holes exist, and that's a big if, they'd solve the timeline problem neatly. TON 618 wouldn't be a thing that became a black hole. It would be something that was born as one 13.8 billion years ago and has been feeding ever since. We don't know which answer is right. We might never know. What we do know is that TON 618 exists, and its existence forces us to admit that the early universe was building things faster than our models predict. Now let's talk about what a black hole actually does to the space around it. Because calling it a hole is misleading. It's not a hole in the sense of a pit you could fall into. It's a place where space-time itself has been bent so sharply that it forms a one-way trap. Einstein's general relativity describes gravity not as a force, but as the curvature of space-time. Mass tells space-time how to curve. Space-time tells mass how to move. A black hole is what happens when you curve space-time so much that it folds in on itself. The singularity at the centre is a point, or possibly a ring, depending on whether the black hole is spinning, where the curvature becomes infinite. The math breaks. Physics stops giving answers. The event horizon is the boundary where the curvature becomes so steep that escape velocity exceeds the speed of light. Inside that boundary, every path you can take, every direction you can move, leads toward the singularity. Not because something is pulling you, because the geometry of space-time itself only allows motion in one direction, inward. If you were somehow hovering just outside the event horizon of TON 618, which you couldn't be because the tidal forces would tear you apart long before you got that close, time would slow down for you relative to the rest of the universe. This isn't metaphor, it's measurable. Clocks near massive objects tick slower than clocks farther away. Near a black hole, the effect becomes extreme. A minute for you could be hours, days, or centuries for someone far away. The closer you get, the more severe the dilation. At the event horizon itself, time dilation becomes infinite. To an outside observer, you would appear to freeze at the horizon, your light redshifting into invisibility as you asymptotically approach the boundary without ever quite crossing it. From your perspective, assuming you survived, you'd cross the horizon in finite time and continue falling toward the singularity. Both perspectives are correct. That's general relativity. The tidal forces are what kill you. Tidal forces are the difference in gravitational pull between your head and your feet. Near Earth, that difference is negligible. Near a black hole, it's lethal. The closer you get, the stronger the gradient. At some point, the pull on your feet becomes so much stronger than the pull on your head that the difference exceeds what your body can withstand. You get stretched. The technical term is spaghettification. Your body elongates into a thin stream of atoms, each pulled apart from its neighbours by the differential gravity, until you're no longer a coherent object, just a string of particles spiralling toward the singularity. For stellar mass black holes, spaghettification happens well outside the event horizon. For supermassive black holes like TON 618, the tidal gradient near the horizon is gentler because the horizon is so much larger. You could, in theory, cross the event horizon of TON 618 and survive for a brief moment before the tidal forces deeper in finally pulled you apart. Not that it helps. Once you're inside, there's no coming back. Black holes don't just warp space, they warp light. Gravitational lensing is the bending of light by mass, and near a black hole the effect is extreme. Light passing close to the event horizon gets bent into tight curves. Some of that light can orbit the black hole multiple times before either escaping or falling in. If you were hovering near TON 618 and looking outward, you'd see the entire universe compressed into a shrinking circle above you. Behind you, where the black hole sits, you'd see nothing. No distortion, no glow, just an absence so complete your brain would struggle to process it as an object. A perfect black circle eating the stars. And yet, for all their violence, black holes are also builders. They don't just destroy, they shape. The energy released by a feeding black hole, the radiation and jets of particles blasted outward at near light speed, can regulate the growth of the galaxy around it. That feedback mechanism is one of the most important processes in galaxy evolution. When a black hole feeds, it heats the gas in the surrounding galaxy. Hot gas is harder to compress, which means it's harder for that gas to collapse and form new stars. In the most extreme cases, the radiation and jets from an active black hole can drive powerful winds that blow gas out of the galaxy entirely, shutting down star formation for millions of years. Astronomers call this quenching. It's one of the main reasons why the biggest galaxies in the universe stopped making stars billions of years ago. Their central black holes grew so massive and fed so aggressively that they ejected or heated all the available gas, leaving behind dead galaxies full of old red stars and nothing else. TON 618 is doing this right now. The light we see is the galaxy in the process of being quenched. The quasar phase doesn't last forever. Eventually, the black hole runs out of nearby gas. The accretion disk fades, the jets shut off. What's left is a dormant supermassive black hole sitting at the centre of a galaxy that has stopped growing. Our own Milky Way's black hole is in that dormant state. It's still there, still massive, but it's not feeding. There's no accretion disk, no jets, no brilliant glow, just a quiet gravitational anchor holding the galaxy together. Every large galaxy we've ever studied has a supermassive black hole at its centre. The correlation between black hole mass and galaxy mass is one of the tightest relationships in astrophysics. Bigger galaxies have bigger black holes. The ratio is surprisingly consistent. About 1/1000th of the galaxy's total stellar mass ends up in the central black hole. Nobody knows why. The black hole's gravity only dominates the very centre of the galaxy. It shouldn't be able to regulate what happens tens of thousands of light years away. And yet the correlation holds. That relationship suggests that black holes and galaxies grow together, feeding off the same gas reservoirs, shaping each other through feedback processes we're only beginning to understand. TON 618 didn't grow in isolation. It grew inside a galaxy, pulling in gas, heating its surroundings, driving winds, shaping the star formation history of everything nearby. The galaxy around TON 618, which we can barely see because the quasar outshines it by such a huge margin, is a massive elliptical, probably one of the largest galaxies in its region of the universe. And it got that way in part because the black hole at its centre ate everything. There's a limit to how big black holes can get. At least there should be. The more massive the black hole, the more energy it releases when it feeds, and the harder it becomes to pull in fresh gas. At some point, the feedback becomes so strong that further growth stops. The exact limit depends on how gas is supplied to the black hole, how efficiently the black hole converts mass into radiation, and how much of that radiation escapes versus getting absorbed by surrounding material. Current models suggest that black holes much larger than 100 billion solar masses should be extremely rare, possibly impossible. TON 618 is already halfway to that limit, and it formed in less than 4 billion years. If the universe keeps running, if galaxies keep merging and black holes keep finding ways to feed, we might eventually see even larger ones. Or we might not. We might be looking at TON 618 during a brief window in cosmic history, when the conditions for building supermassive black holes were uniquely favourable, and nothing like it will ever form again. Either way, TON 618 is not just a record holder, it's a test case, a challenge to our models. A data point sitting at the extreme end of the distribution, forcing theorists to either explain how it got there or admit that something in the physics is missing. And it's only one object, one black hole. The universe contains billions of galaxies, and most of them have supermassive black holes at their centres. Most are smaller than TON 618, but some are close. Phoenix A, another ultramassive black hole, weighs in at around 100 billion solar masses, though that estimate is disputed. IC 1101, the largest known galaxy, almost certainly harbours a black hole weighing tens of billions of solar masses. We just haven't measured it precisely yet. These objects exist. They're out there right now, warping space-time, shaping galaxies, anchoring the structure of the universe at the largest scales, and they started as something smaller: seeds, collapsed stars, or primordial density fluctuations, or direct collapse objects. Whatever they were, they grew, and in growing they built the scaffolding on which everything else hangs. If you want to understand the Hercules-Corona Borealis Great Wall, a structure 10 billion light-years long, you have to understand the pieces it's made of. Black holes are the anchors, galaxies are the building blocks, and the largest galaxies in the universe, the ones that serve as the nodes in the cosmic web, are so massive, so old and so strange that they make our own Milky Way look like a rounding error. Let's talk about those. We just spent time talking about the densest objects in existence, points of infinite collapse where the universe folds in on itself. Now we need to zoom out, because black holes, even the biggest ones, are still just seeds, anchors, the gravitational centres around which something much larger assembles. If you want to understand structures 10 billion light-years wide, you first have to understand the building blocks. The islands of light floating in the dark, the collections of hundreds of billions of stars held together by gravity and dark matter, spinning through the void like cities made of fire. We need to talk about galaxies, and we need to talk about the biggest one we've ever found. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter. That's the textbook definition. It tells you almost nothing useful. A better definition might be this. A galaxy is what happens when gravity and time work together on clouds of hydrogen left over from the Big Bang. The gas clumps, the clumps collapse, stars ignite, those stars explode and seed the next generation with heavier elements. Planets form, moons form. In at least one case, something wakes up on one of those planets and starts asking questions about how it all fits together. Galaxies come in three main types, though like most categories in astronomy, the boundaries are fuzzy and there are plenty of things that don't fit cleanly into any box. Spiral galaxies are the ones that show up in posters and science fiction movies. Flat rotating disks with arms that curl outward from a central bulge. Our Milky Way is a spiral galaxy. So is Andromeda. The arms are not solid structures, they're density waves, regions where stars and gas bunch up temporarily as they orbit the galactic centre. The arms appear bright because that's where new stars are forming, hot blue giants that live fast and die young. Spiral galaxies tend to be younger, more active, still making stars from their reservoirs of cold gas. Elliptical galaxies are the opposite. They're shaped like footballs or stretched spheres, with no disk, no spiral arms, and very little ongoing star formation. Most of their gas has either been used up or blown away. What's left is a swarm of old red and yellow stars orbiting the galactic centre in random directions. Elliptical galaxies range in size from dwarfs smaller than the Milky Way to giants that dwarf everything else. The biggest galaxies in the universe are all ellipticals, and they got that way by eating their neighbours. Irregular galaxies are the misfits. No clear structure, no symmetry, just a chaotic blob of stars and gas. Some are small galaxies distorted by the gravity of a larger neighbour. Others are the wreckage of collisions, galaxies in the process of merging or being torn apart. The large and small Magellanic Clouds, two small galaxies orbiting the Milky Way, are irregular. In a few billion years, they'll probably be absorbed entirely, their stars scattered into our galaxy's halo. There's a fourth category that doesn't get talked about as much: lenticular galaxies. These sit somewhere between spirals and ellipticals. They have a disk like a spiral galaxy, but no arms and almost no star formation. They're the in-between cases, galaxies that have used up their gas but still retain the flattened structure of a rotating disk. Astronomers argue about whether they're old spirals that ran out of fuel or ellipticals that happen to form with some residual rotation. Probably both, depending on the galaxy. And then there are the monsters, the galaxies so large they break the normal classification system. Astronomers call them supergiant ellipticals, or sometimes CD galaxies, short for central dominant. They sit at the centres of massive galaxy clusters, having grown fat by cannibalising everything around them. They're not just bigger than normal ellipticals. They're fundamentally different, with extended halos of stars stretching far beyond what you'd expect from a single galaxy's formation history. IC 1101 is one of those monsters. Depending on which source you trust, it might be the largest galaxy ever found. And just like with TON 618, the numbers are so extreme that the first time you hear them, your brain refuses to process them as real. Let's start with the name. IC stands for Index Catalogue, a supplement to the new General Catalogue of Nebulae and Star Clusters, compiled in the late 1800s. The catalogues were attempts to organise the fuzzy patches of light visible through telescopes at the time. Most of those patches turned out to be galaxies, though nobody knew that yet. The term galaxy itself in the modern sense wasn't widely used until the 1920s, when Edwin Hubble finally proved that these nebulae were separate island universes far beyond the Milky Way. IC 1101 was discovered by William Herschel on June 19, 1790. Herschel was a German-born British astronomer who spent decades systematically scanning the sky with increasingly large telescopes, cataloguing thousands of objects. He didn't know what IC 1101 was. He couldn't have. It was just another faint smudge in the constellation Virgo. It would take more than a century before astronomers realised how far away it was, and what that distance implied about its size. IC 1101 sits at the centre of a galaxy cluster called Abell 2029, roughly 1.15 billion light-years from Earth. That's not as far as TON 618, but it's still deep into the universe's middle age. The light we see left IC 1101 when the universe was about 84% of its current age. Earth existed. The Sun existed. Life had been around for billions of years. Dinosaurs had already come and gone. Mammals were spreading across the continents, and in a cluster of galaxies more than 1 billion light-years away, the largest galaxy in that cluster was quietly growing, pulling in stars from its neighbours, adding mass year after year in a process that had been running for billions of years and shows no sign of stopping. Now let's talk about the size. This is where things get messy because different sources give wildly different numbers, and the disagreement comes down to what you mean by the edge of a galaxy. Galaxies don't have sharp boundaries. They fade. The density of stars drops off gradually as you move outward from the centre. At some point the density gets low enough that you stop calling it part of the galaxy and start calling it intergalactic space. But where you draw that line is somewhat arbitrary. Do you measure to the point where the density drops to a certain threshold? Do you measure to the outermost detectable star? Do you include the halo of dark matter that surrounds every galaxy, but can't be seen directly? Some sources list IC 1101's diameter at around 400,000 to 550,000 light-years. That's already enormous. The Milky Way is roughly 100,000 light-years across. IC 1101, by this measure, would be 4 to 5 times wider. Big, but not unimaginable. Other sources list the diameter at closer to 4 million light-years. That number comes from measuring the full extent of the galaxy's stellar halo, the faint outer envelope of stars that extends far beyond the bright central core. If you use that definition, IC 1101 is 40 times wider than the Milky Way. 40 times. You could line up the Milky Way end to end 40 times and still not match the span of IC 1101's halo. 4 million light-years is a distance so large that it stops feeling like a single object and starts feeling like a region of space. For comparison, the Andromeda Galaxy, our nearest large neighbour, is about 2.5 million light-years away. IC 1101's diameter is larger than the distance between us and Andromeda. Imagine a galaxy so wide that if you placed it where the Milky Way is, it would reach past Andromeda and keep going. The confusion over the size isn't a mistake or a controversy in the usual sense. It's a reflection of the fact that IC 1101 is not a normal galaxy. It's a CD galaxy, a central dominant elliptical sitting in the middle of a dense cluster where galaxies are constantly interacting. Over billions of years, IC 1101 has pulled in stars from smaller galaxies that wandered too close. Those stars don't stay in tight orbits, they get scattered into wide, diffuse halos. The result is a galaxy with a bright core maybe a few 100,000 light-years across, surrounded by a vast extended envelope of stars stretching millions of light-years in every direction. So when someone asks how big IC 1101 is, the answer depends on what you're measuring. The core, 500,000 light-years, the full halo, 4 million light-years. Both numbers are correct. Both are describing the same object. Let's talk about what's inside. IC 1101 contains an estimated 100 trillion stars. 100 trillion. For comparison, the Milky Way has somewhere between 100 billion and 400 billion stars depending on whose estimate you trust. IC 1101 has at least 250 times more stars than our entire galaxy. Some estimates put it closer to 1,000 times more. 100 trillion stars means 100 trillion individual suns, each potentially surrounded by planets, moons, asteroids, comets. If even a tiny fraction of those stars have planets, and current evidence suggests most stars do, then IC 1101 contains trillions upon trillions of worlds, some rocky, some gas giants, some in the habitable zone where liquid water could exist, some with moons that might harbour subsurface oceans. The odds that none of those worlds ever developed life are essentially zero. Life on Earth appeared within a few 100 million years of the planet, cooling enough to support liquid water. If that timeline is anywhere close to typical, then IC 1101 almost certainly contains billions of planets where life has emerged at some point in the galaxy's history. Some of those planets might have developed complex life, some might have developed intelligent life, some might have built civilizations, technologies, spacecraft, and none of it matters, because IC 1101 is more than 1 billion light-years away. And even if there were a thriving interstellar civilization in that galaxy right now, we would never know. The light reaching us today left IC 1101 a billion years ago. If there's anyone there looking back at us, they're seeing Earth as it was 1 billion years ago, long before anything more complex than single-celled organisms existed on land. We are looking at each other's pasts across a gulf of space-time so vast that communication even at the speed of light would take longer than most species survive. But we're not here to speculate about alien civilizations. We're here to understand how a galaxy gets this big in the first place. Galaxies grow in 2 main ways. They pull in gas from their surroundings and form new stars, a process called accretion. And they collide with other galaxies and merge, a process that sounds violent but is actually surprisingly gentle at the scales involved. When 2 galaxies collide, the stars themselves almost never hit each other. Space is mostly empty. Even inside a galaxy, the distances between stars are enormous compared to the size of the stars themselves. If you scaled the Sun down to the size of a basketball, the nearest star would be about 6,000 kilometers away. When galaxies merge, the stars pass through each other like 2 swarms of bees interpenetrating. Occasionally, 2 stars might pass close enough to perturb each other's orbits, but direct collisions are vanishingly rare. What does collide is the gas. Galaxies contain vast clouds of hydrogen and helium drifting between the stars. When 2 galaxies merge, those gas clouds smash into each other at hundreds or thousands of kilometers per second. The collisions compress the gas, triggering enormous bursts of star formation. For a few 100 million years, the merging system lights up with thousands of massive young stars, bright blue giants that burn through their fuel in a few million years and explode as supernovae. Then the gas runs out, the starburst fades, and what's left is a larger, redder, quieter galaxy. IC 1101 has been through this process dozens, possibly hundreds of times. Every smaller galaxy that wandered into the Able 2029 cluster and got too close to IC 1101's gravitational pull ended up being torn apart and absorbed. The stars from those smaller galaxies now orbit IC 1101's core in chaotic, elongated paths, forming the extended halo that makes the galaxy so large. The gas from those galaxies either formed stars during the merger, or was heated and blown away by radiation from the central supermassive black hole. That black hole, by the way, is one of the largest known. No one has measured it directly, but based on the correlation between galaxy mass and black hole mass, IC 1101's central black hole probably weighs somewhere between 10 billion and 100 billion solar masses. It might rival TON 618. It might exceed it. We don't know because IC 1101's black hole is dormant. There's no accretion disk, no quasar glow. Just a dark gravitational anchor sitting at the centre of a galaxy that stopped growing billions of years ago. And that's the other key point about IC 1101. It's old. Not just old in the sense that it formed a long time ago, but old in the sense that it's done, finished. Elliptical galaxies like IC 1101 are sometimes called red and dead because they're full of old red stars and have no ongoing star formation. All the gas that could have formed stars has either been used up or ejected. What remains is a fossil, a relic of a more active past, slowly dimming as its stars age and die. Stars don't live forever. The most massive stars, the bright blue giants, live for only a few million years before exploding as supernovae. Mid-sized stars like our Sun live for about 10 billion years. The smallest red dwarfs can live for trillions of years, longer than the current age of the universe. In a galaxy like IC 1101, which hasn't formed new stars in billions of years, all the massive stars are long gone. What's left are the long-lived, low-mass stars. Red dwarfs, orange dwarfs, old yellow stars entering their red giant phase. The galaxy glows with a dull reddish hue, the colour of a population that has aged past its prime. In a few trillion years, assuming IC 1101 doesn't merge with another large galaxy, it will fade even further. The remaining stars will burn out one by one. The red dwarfs will be the last to go, their dim light gradually dimming to nothing over timescales so long that the universe itself will look completely different by then. Eventually IC 1101 will become a graveyard. A halo of dead stars, white dwarfs, neutron stars, black holes, all orbiting a central supermassive black hole in the dark. The universe will still be expanding. The galaxies around IC 1101 will have receded beyond the horizon of detectability, and IC 1101 will be alone, a monument to a time when the universe was young enough for galaxies to grow. But we're not there yet. Right now, IC 1101 is still glowing, still visible, still massive enough to warp the space-time around it, bending the light from more distant galaxies into arcs and rings through gravitational lensing. It's the dominant galaxy in its cluster, the gravitational centre around which hundreds of smaller galaxies orbit. And it's a preview of what the Milky Way might become. Our galaxy is on a collision course with Andromeda. The two galaxies are currently about 2.5 million light-years apart and closing at roughly 110 kilometers per second. In about 4 billion years they'll collide. The merger will take a few 100 million years to complete. During that time, the gas clouds in both galaxies will smash together, triggering a massive starburst. The night sky, assuming Earth is still habitable and anyone is around to see it, will be filled with brilliant new stars and glowing nebulae. Then the gas will run out, the starburst will fade, and what emerges will be a single large elliptical galaxy, sometimes nicknamed Milkomeda. Milkomeda won't be as large as IC 1101, not even close. But it will be bigger than either the Milky Way or Andromeda are now, and it will be red and dead, its star formation history finished. Billions of years after that, if Milkomeda falls into a larger structure like a galaxy cluster, it could be absorbed by an even larger galaxy, its stars scattered into a halo, its identity erased. That's how galaxies like IC 1101 are built. Not in a single event, but through a long accumulation of smaller mergers, each one adding mass, adding stars, adding to the halo. The process is slow by human standards, but fast by cosmic ones. 1 billion years is enough time for dozens of mergers. 10 billion years is enough time for a galaxy to grow from a modest spiral into a supergiant elliptical weighing trillions of solar masses. And here's the thing, IC 1101 is not alone, it's not even unique. Supergiant elliptical galaxies exist at the centres of most massive galaxy clusters. They all form the same way through mergers and accretion, sitting at the bottom of the gravitational well where everything else eventually falls. IC 1101 happens to be one of the largest we've found, but that's partly because it sits in a particularly dense cluster, and partly because it's had a long time to grow. There are probably larger galaxies out there, farther away, too faint or too obscured by dust to have been detected yet. The fact that galaxies this large exist at all tells us something about how the universe is structured. Galaxies don't form in isolation, they form in clusters, and those clusters are themselves part of larger structures. Superclusters, filaments, walls, the cosmic web. If you could see the universe from the outside, if you could somehow step back far enough to see the full three-dimensional distribution of galaxies across billions of light years, you wouldn't see a uniform spread. You'd see a web, filaments of galaxies stretching across the void, connecting dense nodes where clusters sit. Between the filaments, vast empty regions called voids, containing almost nothing. The universe at the larger scales looks less like a smooth fog and more like a sponge, full of holes and threads. IC 1101 sits on one of those threads, a node in the web where matter has concentrated. The Abell 2029 cluster contains hundreds of galaxies, and IC 1101 is the largest, the one that has eaten the most neighbours, the one that sits at the gravitational centre of the whole system. The Milky Way sits on a thread too, a much smaller one. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, is a minor structure compared to something like Abell 2029. But our local group is connected to larger structures, filaments that stretch across tens and hundreds of millions of light years, linking clusters and superclusters into a network that spans the observable universe. And that network, that cosmic web, is not random. It's a reflection of how matter clumped together in the early universe. Tiny density fluctuations in the hot plasma moments after the Big Bang, imprinted in the cosmic microwave background, grew over billions of years into the structures we see today. Dark matter, which makes up about 85% of the matter in the universe, provided the gravitational scaffolding. Regular matter, the stuff that makes stars and planets and people, fell into the dark matter halos and lit up. The result is a universe that looks smooth at small scales, lumpy at medium scales, and structured at the larger scales. Galaxies cluster. Clusters connect into superclusters. Superclusters link into filaments. And the filaments, stretching across billions of light years, form the boundaries of the voids. IC 1101 is one galaxy, one building block. But it's a building block that weighs trillions of solar masses, contains 100 trillion stars, and spans 4 million light years from edge to edge. It's the kind of thing that makes you realise how inadequate our language is for describing the universe. We call it a galaxy, the same word we use for the Milky Way, even though IC 1101 is hundreds of times more massive. We call it large, even though large doesn't begin to cover it. We measure it in light years and solar masses and star counts, and none of those numbers convey the actual scale of what we're talking about. If you were somehow standing on a planet in the outer halo of IC 1101, looking inward toward the core, you wouldn't see a galaxy. You'd see a sky full of stars, denser than the Milky Way's sky, but not dramatically so. The stars in the halo are spread thin, separated by light years. It would take a telescope to see the dense core, a glowing elliptical blob millions of light years away in your own galaxy. You wouldn't feel like you were inside something enormous. You'd just see stars, the same way we see stars from Earth. Scale doesn't announce itself. It hides in the distances between things. But zoom out, step back, look at IC 1101 from a billion light years away, and the scale becomes undeniable. A single galaxy larger than the distance between the Milky Way and Andromeda. A single object containing more stars than 100 Milky Ways. A single structure built over billions of years through a slow accumulation of smaller galaxies, each one torn apart and absorbed, its stars scattered into the growing halo. This is what the universe builds when you give it time. This is the scale at which gravity operates when you're patient enough to let it work. And this is only one galaxy, one node in the web. There are billions of galaxies in the observable universe, and most of them are connected to something larger. Our Milky Way, for instance, is part of something called the local group. The local group is part of something called the Virgo supercluster. And the Virgo supercluster, it turns out, is just a small piece of a much larger structure that wasn't even fully mapped until the 2010s. A structure so vast that it redefines what we mean when we talk about home. That structure has a name, and understanding it means understanding how galaxies like IC 1101 fit into the larger cosmic web, how matter is distributed across hundreds of millions of light years, and why the universe looks the way it does when you step back far enough to see the whole picture. We need to talk about where we actually are. Not just in space, but in the architecture of the universe itself. We need to talk about the supercluster that contains us, the filaments that connect it to everything else, and the voids that define the boundaries of structure, we need to talk about Laniakea. We just talked about IC 1101, a galaxy so massive it contains 100 trillion stars and stretches 4 million light-years across. A galaxy that sits at the centre of a cluster, the dominant gravitational anchor around which hundreds of smaller galaxies orbit. But IC 1101 is not floating alone in some empty corner of space. It's part of something larger, a structure, a network. And that network extends so far and connects so many galaxies that calling IC 1101 large starts to feel like calling the ocean damp. Every galaxy we've ever observed is part of this network, including ours. The Milky Way, our home galaxy with its few hundred billion stars, sits on a thread in a web that stretches across hundreds of millions of light-years. For most of the 20th century, astronomers thought they had a decent handle on where we fit in that web. We were part of the Virgo supercluster, a collection of galaxy groups and clusters centered on the massive Virgo cluster, about 50 million light-years away. That was our neighborhood. That was our address. Then in 2014, a team led by astronomer Brent Tully at the University of Hawaii published a paper that redrew the map. They showed that the Virgo supercluster wasn't actually the largest structure we belonged to. It was just a piece of something much bigger. A basin of gravitational attraction spanning more than 500 million light-years, containing more than 100,000 galaxies, with a combined mass of about 100 quadrillion suns. They named it Laniakea, a Hawaiian word meaning immeasurable heaven, or depending on the translation, open skies. The name fits. Because once you understand what Laniakea is and how it was discovered, the universe stops feeling like a collection of separate objects and starts feeling like a single connected system. A vast flowing structure where every galaxy, including ours, is being pulled along currents we can't see toward destinations we're only beginning to map. Let's back up, start smaller. Because to understand superclusters like Laniakea, you first need to understand the hierarchy, the cosmic ladder. Galaxies don't exist in isolation, they clump, and the clumps themselves clump, and those clumps connect into even larger structures. It's a nested system, and each level has a name. At the bottom you have individual galaxies, spirals, ellipticals, irregulars, islands of stars floating in the dark. The Milky Way is one galaxy. Andromeda is another. Each one contains anywhere from a few million to a few trillion stars, depending on size. Galaxies group together into galaxy groups. A galaxy group is a small collection, usually a few dozen galaxies or fewer loosely bound by gravity. The Milky Way belongs to something called the local group, which contains about 50 galaxies. Most of them are dwarfs, small irregular galaxies with only a few billion stars. The two dominant members of the local group are the Milky Way and Andromeda. Everything else is orbiting one of those two, getting pulled around by their gravity, waiting to be absorbed. Galaxy groups merge and gather into galaxy clusters. A galaxy cluster is bigger, denser, and more tightly bound than a group. Clusters contain hundreds or thousands of galaxies packed into a region a few million light-years across. The Virgo cluster, for instance, contains more than 2,000 galaxies. The Coma cluster contains more than 1,000. These clusters are held together not just by the gravity of the galaxies themselves, but by massive halos of dark matter, the invisible scaffolding that makes up most of the mass in the universe. And clusters don't sit alone either. They gather into superclusters. A supercluster is a collection of galaxy clusters and groups linked together by gravity and spread across tens or hundreds of millions of light-years. Superclusters are not tightly bound the way clusters are. The galaxies in a supercluster are not all orbiting a common center. They're connected by weaker gravitational threads, part of a larger flow of matter moving through space. For decades, astronomers mapped superclusters by eye. They looked at the positions of galaxies on the sky, noticed where they clustered, and drew boundaries around regions that looked over-dense. The Virgo supercluster was defined that way. So was the Hydra Centaurus supercluster. So were dozens of others. It was a reasonable approach given the data available, but it had a problem. Positions on the sky don't tell you how galaxies are actually moving. They tell you where things are, not where they're going. And in a dynamic universe where everything is being pulled by gravity and pushed by the expansion of space, motion matters. Brent Tully and his team took a different approach. Instead of mapping where galaxies are, they mapped where galaxies are going. They measured the velocities of thousands of galaxies within a few hundred million light-years of the Milky Way, using redshifts and Doppler shifts to determine how fast each galaxy was moving and in what direction. Then they subtracted out the overall expansion of the universe, the Hubble flow, which carries everything away from everything else as space itself expands. What's left after you subtract the expansion is called peculiar velocity, the motion of a galaxy relative to the average flow. Peculiar velocities are caused by gravity. Galaxies move toward regions of higher mass and away from regions of lower mass. By mapping those motions, Tully's team could trace the gravitational flow of the universe, the currents pulling galaxies through space like water flowing downhill. The result was a map unlike anything astronomers had seen before. Not a map of positions, but a map of basins of attraction. Regions where galaxies are all flowing toward a common gravitational center. The Milky Way, it turned out, is part of a basin that extends far beyond the old boundaries of the Virgo supercluster. The Virgo cluster is not the center. It's just one dense node along the way. The real center, the place toward which everything in our basin is flowing, is a region called the Great Attractor. The Great Attractor is not a single object. It's a massive overdensity of galaxies and dark matter sitting about 200 million light-years away in the direction of the constellations Hydra and Centaurus. We can't see it directly because it sits behind the plane of the Milky Way, obscured by dust and stars in our own galaxy. But we can measure its gravitational pull. Every galaxy within hundreds of millions of light-years, including ours, is being pulled toward it. The Milky Way is moving through space at about 600 kilometers per second, and a significant fraction of that motion is due to the gravity of the Great Attractor and the even larger structures beyond it. The basin of attraction that flows toward the Great Attractor is Laniakea. It's not a thing you can point to and say, there it is. It's a region of space defined by motion. If your galaxy is flowing toward the Great Attractor, you're in Laniakea. If your galaxy is flowing away or toward a different center, you're not. The boundary is not a wall or a surface, it's a watershed, the line where the gravitational flow divides and starts moving toward a different attractor. Laniakea spans roughly 160 megaparsecs. A megaparsec is about 3.26 million light-years. 160 megaparsecs is about 520 million light-years. If you could take a sphere centered on the Milky Way and extend it out to a radius of 260 million light-years, you'd be looking at the rough extent of Laniakea. Inside that sphere are more than 100,000 galaxies. Galaxy groups, galaxy clusters, filaments of gas and dark matter, and vast voids where almost nothing exists. The total mass of all that structure is about 100 quadrillion times the mass of our Sun. That's 10 to the 17th solar masses, a number so large it stops meaning anything unless you stack it against other incomprehensible numbers. For comparison, the Milky Way weighs somewhere between 800 billion and 1.5 trillion solar masses, depending on how much dark matter you include. Laniakea contains roughly 100,000 galaxies, each weighing anywhere from a few billion to a few trillion solar masses. The math checks out. 100,000 galaxies times an average mass of a trillion solar masses gives you roughly 100 quadrillion solar masses. That's Laniakea. That's home, at the largest scale we can meaningfully define. The name, Immeasurable Heaven, was chosen because Tully and his collaborators wanted something that honoured the heritage of Polynesian navigation. Hawaiian astronomers have a long tradition of wayfinding, of using the stars to navigate across vast stretches of ocean. Laniakea is in some sense our cosmic ocean, the region of space we're travelling through, pulled by currents we can measure but not control. Here's the uncomfortable part. Laniakea is not the largest structure, it's just the one we're inside. The Great Attractor itself is being pulled towards something even larger. There's a massive concentration of galaxy clusters sitting about 650 million light-years away called the Shapley supercluster. The Shapley supercluster is one of the most massive structures in the nearby universe, weighing roughly 10 quadrillion solar masses, about 10 times the mass of Laniakea. Everything in our region of space, including Laniakea, is being pulled toward it. That motion is slow. 600 kilometers per second sounds fast, and by everyday standards it is. But at the scale of hundreds of millions of light-years, it's glacial. The Milky Way will take tens of billions of years to reach the Shapley supercluster, assuming it ever does. The expansion of the universe is accelerating, driven by dark energy, and that acceleration is pushing distant structures away from us faster than gravity can pull us together. It's possible that the Milky Way and the Shapley supercluster will never actually merge. The expansion might win, the distance might grow faster than we can close it. In that case, we'll spend the rest of eternity drifting towards something we'll never reach, pulled by a gravity that can't quite overcome the stretching of space itself. But we're not here to talk about the heat death of the universe. We're here to talk about structure, about how matter organises itself across the larger scales, and the answer is not random. The universe is not a fog of evenly distributed galaxies. It's a web. Astronomers call it the cosmic web, and the name is almost too literal. If you could see the full three-dimensional distribution of galaxies across 1 billion light-years, you would see something that looks exactly like a web. Long, thin filaments of galaxies stretching across space, connecting dense nodes where galaxy clusters sit. Between the filaments, enormous empty regions called voids, containing almost no galaxies at all. The whole structure looks organic, like something grown rather than built. And in a sense, it was grown. Gravity, acting over billions of years on tiny density fluctuations left over from the Big Bang, pulled matter together along certain lines, creating the filaments, and left the voids empty. Filaments are the highways of the cosmic web. They're long, thread-like structures, sometimes stretching hundreds of millions of light-years, connecting one galaxy cluster to another. The galaxies inside a filament are not randomly distributed. They're strung out along the length of the filament like beads on a string, flowing along the gravitational gradient toward the densest regions at either end. Filaments contain not just galaxies, but vast clouds of hot gas, dark matter halos, and magnetic fields threading through the structure. Most of the matter in the universe, at the larger scales, is either in filaments or at the nodes where filaments intersect. Nodes are the densest regions, the places where multiple filaments meet. Galaxy clusters sit at the nodes. Superclusters are collections of nodes linked by filaments. Laniakea is one such collection. The Great Attractor is one of the nodes. The Virgo cluster is another. The filaments connecting them carry galaxies inward, funneling matter toward the densest regions where gravity is strongest. Voids are the opposite. They're enormous underdense regions, sometimes spanning hundreds of millions of light-years, where galaxies are rare or absent entirely. Voids are not completely empty. There are a few galaxies scattered through them, usually small irregular dwarfs drifting in isolation. But compared to the filaments and nodes, voids are deserts. The matter that could have filled them has been pulled away by gravity, evacuated over billions of years as the cosmic web formed. The voids define the structure as much as the filaments do. If you removed the voids, the filaments and clusters would lose their shape. The cosmic web exists because matter clumped in some places and was left behind in others. The contrast is what makes the pattern visible. There's a strange beauty to this. The universe, at the larger scales, is almost fractal. Small structures nest inside larger ones. Galaxies cluster. Clusters link into superclusters. Superclusters trace filaments. Filaments connect across the observable universe. And all of it, every piece of structure, every filament and void and node, grew from the same starting point. Tiny quantum fluctuations in the density of matter and energy moments after the Big Bang, imprinted in the fabric of space-time, amplified over 13.8 billion years by gravity and the expansion of space. We can see those fluctuations today. The cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old, contains tiny temperature variations, hot spots and cold spots, each representing a region where the density of matter was slightly higher or slightly lower than average. Those variations are tiny, only about 1 part in 100,000. But they're real, and they're the seeds of everything that came after. Hot spots became overdense regions where matter clumped together. Cold spots became underdense regions where matter was pulled away. Over billions of years, the overdense regions grew into galaxy clusters and filaments. The underdense regions became voids. The cosmic web is a direct consequence of those initial fluctuations. The map of the universe today is a magnified, stretched, evolved version of the map that existed when the universe was less than 500,000 years old. The pattern was already there, written into the distribution of matter and energy moments after the Big Bang. Gravity just turned up the contrast. Laniakea fits into that web. It's one supercluster among thousands, maybe millions, spread across the observable universe. We've mapped a few nearby superclusters in detail. The Shapley supercluster, as already mentioned, is one of the largest nearby concentrations. The Perseus Pisces supercluster is another. The Coma supercluster, the Hercules supercluster. Each one is a massive structure containing thousands of galaxies, connected to its neighbours by filaments, separated by voids. The Shapley supercluster is particularly interesting because it's so massive. 10 quadrillion solar masses makes it one of the largest concentrations of matter within a billion light-years. It's dense enough and close enough that its gravity affects the motion of everything around it, including Laniakea. Astronomers have known about the Shapley supercluster since the 1930s, when Harlow Shapley, the astronomer it's named after, first noticed an overdensity of galaxies in that region of the sky. But its full extent and mass weren't clear until much later, after redshift surveys allowed astronomers to measure distances and map the three-dimensional structure. Another notable structure is the Phoenix supercluster, though it's farther away and less well studied. The Phoenix supercluster sits roughly 570 million light-years from Earth and is one of the most massive superclusters known. It contains several large galaxy clusters, including the Phoenix cluster itself, which harbours one of the most massive galaxy clusters ever found. The Phoenix cluster's central galaxy is a supergiant elliptical, similar to IC 1101, and it's actively forming stars at a rate of several hundred solar masses per year. That's unusual for a galaxy its size. Most supergiant ellipticals stopped forming stars billions of years ago. The Phoenix cluster is a rare example of a system still growing, still feeding, still active. These superclusters, Laniakea, Shapley, Phoenix, and all the others, are the largest gravitationally bound or semi-bound structures in the universe. Anything larger is dominated by the expansion of space. Anything smaller is collapsing under its own gravity. Superclusters sit right at the boundary, the largest scale at which structure holds together against the pull of cosmic expansion. And here's where things get interesting. Because superclusters are not the largest structures we've found. There are patterns in the distribution of galaxies that extend even farther. Filaments that stretch not hundreds of millions of light-years, but billions of light-years. Walls and sheets of galaxies, thin planar structures connecting distant clusters, spanning distances so large they challenge the assumptions baked into our cosmological models. The cosmological principle, the idea that the universe is homogeneous and isotropic on the larger scales, says that if you average over large enough volumes, the universe should look the same everywhere. No preferred direction, no giant structures that dominate the distribution of matter. The principle works mostly. Average over a few hundred million light-years, and the universe does look smooth. But average over smaller volumes, or look at specific regions and you find exceptions. Structures that seem too large, too coherent, too organised to fit comfortably into the models. The Sloan Great Wall, discovered in 2003, is one example. It's a filament of galaxies stretching roughly 1.3 billion light-years across, one of the largest known structures at the time of its discovery. The Sloan Great Wall connects several superclusters and traces a region of unusually high galaxy density. It's not a solid wall in any physical sense, it's a statistical feature, a region where galaxies are more tightly packed than in the surrounding space. But it's real, and it's big enough that when it was discovered, some astronomers started asking uncomfortable questions about whether the cosmological principle actually holds at all scales. Then there's the Hercules-Corona Borealis Great Wall, the structure we're building toward. A filament, or cluster of filaments, or possibly a statistical artifact depending on who you ask, stretching roughly 10 billion light-years across the sky. If it's real, if it's actually a coherent structure, and not just an illusion created by the way we're sampling the data, it's the largest thing in the universe, and its existence is a direct challenge to the cosmological principle. Because the cosmological principle has a limit. Structures larger than about 1.2 billion light-years shouldn't exist. That limit comes from the physics of how the universe evolved. After the Big Bang, matter was distributed almost uniformly, with only tiny variations in density. Those variations grew over time as gravity pulled matter together, but the process is slow. The denser a region is, the more matter it attracts, and the faster it grows. But there's only so much time. The universe is 13.8 billion years old. Structures can only grow so large in that span. The math says that anything larger than about 1.2 billion light-years shouldn't have had time to form. Gravity simply hasn't had enough time to pull matter together across distances that large. And yet we keep finding structures that exceed that limit. The Sloan Great Wall is bigger than the limit. The Hercules-Corona Borealis Great Wall is nearly 10 times bigger. If these structures are real, something in our understanding of how the universe forms structure is incomplete. Either the initial density fluctuations were lumpier than we thought, or gravity worked faster in the early universe than the models predict, or we're misinterpreting the data and what looks like a single coherent structure is actually multiple unrelated features aligned by chance. That's the debate we're walking into. And to understand the debate, to see why the Hercules-Corona Borealis Great Wall matters, you first need to understand the tools astronomers use to find these structures and the assumptions baked into those tools. Mapping the universe is hard. Galaxies are faint. Distant galaxies are fainter. The farther away something is, the more its light has been redshifted by the expansion of the universe, stretching the wavelengths into the infrared or even radio spectrum. To map large-scale structure, astronomers conduct redshift surveys. They point telescopes at patches of sky, measure the spectra of thousands or millions of galaxies, determine each galaxy's redshift, and convert that redshift into a distance. The result is a three-dimensional map showing where galaxies are located in space. Redshift surveys have revealed the cosmic web. They've shown us the filaments, the voids, the clusters, the superclusters. Every structure we've talked about, from the local group to Laniakea to the Shapley supercluster, was mapped using redshift surveys. But those surveys are incomplete. Telescopes can only see so far. Faint galaxies get missed. Regions obscured by dust or foreground stars are harder to survey. And even the largest surveys only cover a fraction of the sky. The Hercules-Corona Borealis Great Wall was found using gamma-ray bursts, not galaxies. Gamma-ray bursts are the afterglows of exploding stars, visible across billions of light-years. They're rare and randomly distributed, but when you find a cluster of them at the same distance, it suggests there's a concentration of galaxies in that region. The Great Wall was inferred from the positions of gamma-ray bursts, not directly observed as a continuous structure. That's why the debate exists. Some astronomers think the clustering of gamma-ray bursts is real and reflects an underlying structure. Others think it's a statistical fluke, an artifact of small sample sizes and the patchy coverage of the surveys. Resolving that debate requires more data, better surveys, and a clearer understanding of how gamma-ray bursts trace the distribution of galaxies. But whether or not the Hercules-Corona Borealis Great Wall is real, the fact that we're asking the question tells you something important. We've reached the edge of the map. The structures we're finding now are so large, so extreme, that they push up against the limits of what our models allow. We're not just cataloguing the universe anymore. We're testing whether the rules we've been using to understand it are actually correct. Laniakea is the foundation. It's the structure we know is real because we've measured the flows, mapped the galaxies, traced the gravitational currents. It's our neighbourhood, our cosmic home, the basin of space we're drifting through as the universe expands around us. But Laniakea is just one piece of a web that extends across the entire observable universe. A web of filaments and voids, nodes and basins, stretching 10 billion light-years or more, connecting everything to everything else in patterns we're only beginning to decode. And somewhere in that web, in a patch of sky near the constellations Hercules and Corona Borealis, there is something that doesn't fit. Something so large, so anomalous, that if it's real, it forces us to rethink the rules. That's where we're going next, to the structure that shouldn't exist, to the Herculean anomaly. We just spent considerable time walking through the hierarchy. Galaxies, clusters, superclusters, filaments. The cosmic web stretching across hundreds of millions of light-years, connecting everything in patterns we're still learning to read. Laniakea, our own supercluster, spans 520 million light-years and contains 100,000 galaxies. The Shapley supercluster, even larger, weighs 10 quadrillion solar masses and sits 650 million light-years away. Structures so massive that when you first hear about them, your brain tries to file them under science fiction because there's no category in everyday experience that fits. And yet all of those structures, every supercluster we've mapped, Every filament we've traced fits comfortably inside the predictions of our cosmological models. They're large, yes. Extreme, certainly. But they're allowed. The math works. Gravity acting over 13.8 billion years on the density fluctuations left over from the Big Bang can build structures that size. The models predicted them before we found them. When redshift surveys revealed the cosmic web in the 1980s and 90s, astronomers were surprised by how well the observations matched the simulations. The universe was doing exactly what it was supposed to do. Then in 2014, a team of astronomers published a paper describing something that wasn't supposed to do. A structure inferred from the positions of gamma-ray bursts, stretching across a patch of sky near the constellations Hercules and Corona Borealis. The initial estimates put the size at somewhere between 2,000 and 3,000 megaparsecs. A megaparsec, remember, is about 3.26 million light-years. 2,000 megaparsecs is roughly 6.5 billion light-years. 3,000 megaparsecs is close to 10 billion light-years. 10 billion light-years, not the diameter of a galaxy, not the span of a supercluster, the length of a single claimed structure, a wall or filament or cluster of filaments running across nearly 11% of the observable universe. They called it the Hercules-Corona Borealis Great Wall. If the structure is real, if it's actually a coherent feature, and not a mirage created by incomplete data or statistical noise, it's the largest thing in the universe, and it should not exist. Let's start with how it was found, because the method matters. The team, led by researchers including Istvan Horvath, John Hackler, and Zsolt Bagoli, was studying gamma-ray bursts. Gamma-ray bursts, or GRBs, are the brightest explosions in the universe. They occur when massive stars collapse into black holes or when neutron stars collide. The burst itself lasts anywhere from a few milliseconds to a few minutes, but during that time, the explosion releases more energy than the Sun will produce in its entire 10 billion year lifetime. For a brief moment, a gamma-ray burst can outshine every other object in its host galaxy combined. GRBs are useful for mapping the universe because they're visible across enormous distances. A supernova, even a very bright one, fades within weeks and becomes difficult to detect beyond a few billion light-years. A gamma-ray burst, by contrast, can be detected from the far edge of the observable universe. Astronomers have spotted GRBs from galaxies more than 13 billion light-years away, from a time when the universe was less than 1 billion years old. If you want to trace the large-scale distribution of matter in the distant universe, GRBs give you a tool that works where almost nothing else does. The catch is that GRBs are rare and randomly distributed. You can't predict where the next one will happen. They occur in galaxies undergoing active star formation, where massive stars are being born and dying in rapid succession. But within that broad category, the specific location and timing of each burst is essentially random. On average, a few GRBs are detected somewhere in the observable universe every day. Over the course of a decade, that adds up to thousands of bursts. Map their positions and distances, and you get a rough sketch of where galaxies are located across billions of light-years. Horvath and his colleagues were analysing a catalogue of gamma-ray bursts detected by the SWIFT satellite and other instruments. They plotted the positions on the sky and calculated the distances based on the redshifts of the host galaxies. Redshift, the stretching of light caused by the expansion of the universe, gives you a direct measure of how far away something is. The more stretched the light, the farther the source, and the further back in time you're looking. When they mapped the GRB positions, they noticed something odd. A tight clustering of bursts in a specific region of the sky, all at roughly the same distance. 14 gamma-ray bursts out of a sample of 31 were concentrated in an area that, statistically, should have contained far fewer. The odds of that clustering being random were calculated at roughly 1 in several million. Not impossible, but uncomfortable. Unlikely enough that it demanded an explanation. The distances to those 14 bursts placed them at redshifts between about 1.6 and 2.1. That corresponds to a time when the universe was between 3 and 4 billion years old, less than a third of its current age, and the angular extent of the clustering on the sky, combined with the distance, implied a physical structure stretching somewhere between 6 and 10 billion light-years, depending on the assumptions used in the calculation. The team published their findings in 2014 in Astronomy and Astrophysics. The paper was cautious. They described the feature as a possible large-scale structure, and noted the statistical significance of the clustering. They did not claim to have definitively proven the existence of a 10 billion light-year wall. They said, here is a pattern in the data that appears significant. Here is what that pattern implies if it's real. Further observations are needed to confirm. The astronomy community responded with a mix of interest and skepticism. Some researchers took the finding seriously and started looking for ways to test it. Others pointed out that GRBs are a sparse and biased tracer of large-scale structure. You're not seeing every galaxy, just the ones that happen to host a gamma-ray burst during the observation window. If the underlying galaxy distribution is patchy, or if there are observational selection effects, you could easily see clustering that doesn't reflect a real coherent structure. In 2015, another analysis by some of the same authors revisited the data with additional GRBs and refined distance estimates. The clustering held. The structure, if it was a structure, remained statistically significant. The estimated size, depending on the method used, ranged from about 7 billion light-years to as much as 10 billion light-years. The uncertainty was large, but even the lower estimates put the feature well beyond the scale of anything that should exist according to standard cosmology. Then in 2020, a further re-examination explicitly framed the problem as both observational and theoretical. The paper acknowledged that the existence of the Hercules-Corona Borealis Great Wall remained unsettled. It could be real, it could be an artifact. The data were consistent with a large structure, but also consistent with a projection effect where multiple, unrelated overdensities along the line of sight appeared to overlap when viewed from Earth. Resolving the ambiguity would require more gamma-ray bursts, better distance measurements, and ideally a direct survey of the galaxies in that region to see whether the overdensity persists when you use a different tracer. As of now, the status of the HCBGW is putative, claimed but not proven, possible but not certain. It sits in that uncomfortable space where the data point towards something, but the interpretation is contested. Some astronomers think it's real, others think it's a statistical fluke amplified by incomplete sampling, and a few think it might be real but not as large as the initial report suggested, closer to a few billion light-years rather than 10. So why does this matter? Why does a disputed clustering of gamma-ray bursts warrant this much attention? Because if the Hercules-Corona Borealis Great Wall is real, if it's actually a coherent structure 10 billion light-years long, it violates one of the foundational principles of modern cosmology. The principle is called the cosmological principle. It states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. No matter where you are in the universe, if you zoom out far enough, the distribution of matter should appear uniform. No giant walls, no enormous voids that dominate the structure, just a smooth, even spread of galaxies, averaged over volumes large enough to wash out the local lumpiness. The cosmological principle is not just a philosophical preference, it's a necessary assumption baked into the equations that describe the expansion and evolution of the universe. Einstein's general relativity allows for many different types of universes, depending on how matter and energy are distributed. A universe that's lumpy at the larger scales would evolve differently than a smooth one. The equations that cosmologists use to calculate the age of the universe, the rate of expansion, the formation of structure, all assume that the cosmological principle holds. If it doesn't, the math changes, and if the math changes, every conclusion we've drawn about the history and future of the universe becomes uncertain. The principle is supported by a mountain of evidence. The cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old, is smooth to an extraordinary degree. The temperature variations are only about 1 part in 100,000. That smoothness tells us the universe was very uniform in its early stages. And large-scale structure surveys, the maps of galaxy distributions across billions of light-years, show that when you average over volumes larger than about 300 to 500 million light-years, the universe does indeed look homogeneous. The lumpiness at smaller scales, the filaments and voids and clusters averages out. The cosmic web starts to look like a uniform fog. But the cosmological principle comes with a scale. It doesn't say the universe is smooth at every scale. It says the universe becomes smooth once you zoom out far enough. The question is, how far is far enough? Different analyses give slightly different answers, But most studies suggest that structures larger than about 1.2 billion light-years should not exist in a universe governed by the standard cosmological model. That number comes from the physics of structure formation. Gravity pulls matter together over time, but the process is limited by how much time has passed since the Big Bang, and how strong gravity is relative to the expansion of space. Run the simulations, plug in the known parameters, and you get a maximum scale for coherent structures. 1.2 billion light-years is the rough consensus. The Sloan Great Wall, discovered in 2003, is about 1.3 billion light-years long. That's right at the edge of the limit. It made people uncomfortable when it was found, but it didn't break the models. It's close enough to the maximum allowed size that you can argue it's a rare statistical fluctuation, an extreme case that's allowed but unlikely. The Hercules-Corona Borealis Great Wall, at 10 billion light-years, is not close to the limit. It's nearly 10 times larger. If it's real, it's not a rare fluctuation. It's an impossibility. The standard model of cosmology, lambda CDM, lambda standing for dark energy and CDM standing for cold dark matter, does not predict structures that large. Gravity hasn't had enough time. The universe hasn't been around long enough for matter to clump together across distances that extreme. The density fluctuations in the early universe, the tiny variations imprinted in the cosmic microwave background, were far too small to seed a structure 10 billion light-years across. There's another way to think about the problem. The cosmological principle implies a scale of homogeneity, a distance beyond which the universe stops being lumpy and starts being smooth. Various studies have tried to measure that scale by analysing galaxy surveys and looking for the point where the clustering signal flattens out. Most estimates put the scale of homogeneity at around 300 to 500 megaparsecs, roughly 1 billion to 1.6 billion light-years. Above that scale, the universe should look smooth. Structures should not persist. The HCBGW, at 3000 megaparsecs or more, is 6 to 10 times larger than the scale of homogeneity. It's a feature that extends well into the regime where features aren't supposed to exist. So if the HCBGW is real, something is wrong. Either the initial conditions in the early universe were lumpier than we thought, or gravity works differently at very large scales, or the expansion history of the universe was different than the models assume, or we're missing some key ingredient in the physics. None of those options are comforting. Each one implies that the standard model, which has worked so well for so many observations, is incomplete in some fundamental way. Let's talk about the initial conditions. The density fluctuations in the early universe, the seeds of all structure, are imprinted in the cosmic microwave background. Astronomers have mapped those fluctuations with extraordinary precision, using satellites like COBE, WMAP and Planck. The fluctuations are tiny, about 1 part in 100,000, and they're distributed across the sky in a pattern that looks random but isn't. The pattern contains information about the physics of the early universe, the amounts of dark matter and dark energy, the rate of expansion, the temperature and density of matter and radiation moments after the Big Bang. The fluctuations follow what's called a power spectrum, a mathematical description of how much structure exists at different scales. The power spectrum measured from the cosmic microwave background matches the predictions of inflation, a theory that says the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretched quantum fluctuations up to cosmic scales, creating the density variations that eventually became galaxies and clusters. The match between theory and observation is so good that inflation has become the leading explanation for why the universe looks the way it does. But the power spectrum also predicts limits. It tells you how much clumping you should see at each scale. Small-scale clumps like galaxies should be common. Large-scale clumps like superclusters should be rarer. Very large-scale clumps like structures bigger than 1 billion light-years should be extremely rare or absent entirely. The HCBGW, if it's real, doesn't fit. It's too large. The power spectrum doesn't have enough power at that scale to build something that big. One way to fix this is to adjust the initial conditions. Maybe the fluctuations were lumpier than the standard models assume. Maybe there were rare, large amplitude fluctuations that don't show up clearly in the cosmic microwave background but were there nonetheless. If the early universe had a few extra large overdensities, gravity could have amplified them over time, building structures larger than the standard predictions allow. This idea isn't crazy. but it requires tweaking the inflation models in ways that are hard to justify without independent evidence. You're adding complexity to explain one observation, which is a red flag. The simpler explanation is usually better, and the simpler explanation here is that the HCBGW isn't real. Another possibility is that gravity behaves differently at very large scales. General relativity, the theory that describes gravity as the curvature of space-time, has been tested extensively at scales ranging from the solar system to galaxy clusters. It works everywhere we've checked. But we've never directly tested it at scales of billions of light years. It's possible that general relativity breaks down or gets modified at those distances, allowing structures to grow larger than the standard predictions. Modified gravity theories exist, and some of them predict stronger clustering at large scales. But most of those theories have problems. They struggle to match other observations, like the rotation curves of galaxies or the bending of light by galaxy clusters. You fix one problem and create three others. It's not a satisfying solution. A third option is that the expansion history of the universe was different. The lambda CDM model assumes that the universe has been expanding at a rate determined by the amounts of matter, and dark energy. Dark energy, the mysterious force driving the accelerated expansion, is assumed to be constant over time, a cosmological constant in Einstein's equations. But what if dark energy wasn't constant? What if it was stronger or weaker in the early universe? A different expansion history would change the timescales for structure formation. Maybe gravity had more time to build large structures because the expansion was slower at certain epochs. Or maybe the expansion was faster, which sounds counterintuitive but could affect the way matter clumped in subtle ways. Testing this idea requires precise measurements of the expansion rate at different times in the universe's history. Astronomers are working on this using supernova, quasars, and other distance indicators. So far, the data are consistent with a constant dark energy, but there are hints of tension. The Hubble constant, the current expansion rate, seems to depend on how you measure it. Some methods give a higher value, others a lower value. That tension might be a clue that something in the expansion history isn't quite right. Or it might just be a measurement problem that will go away with better data. Nobody knows yet. A fourth possibility, and the one many astronomers favour, is that the HCBGW isn't actually a single coherent structure. It might be a projection effect, a chance alignment of several unrelated overdensities that happen to lie along the same line of sight from Earth. Imagine looking at a city skyline from a distance. Some buildings are close together, others are far apart, but from your vantage point they all appear to line up. The same thing can happen with galaxies. If there are 3 or 4 separate clusters or filaments spread across a few billion light-years of distance but all aligned in the same direction, they'd appear to form a single continuous structure when viewed from Earth. The gamma-ray burst would cluster on the sky because the underlying galaxies cluster, but there wouldn't be a single 10 billion light-year wall connecting them. This explanation is appealing because it doesn't require new physics. It's just geometry, perspective, the universe playing tricks on our line of sight. But proving it requires more data. You need to map the region in detail, measure the distances to individual galaxies, and see whether the overdensities are actually connected by a filament or just happen to appear near each other on the sky. That work is ongoing. Future surveys with better instruments and larger samples of galaxies will help settle the question. There's a philosophical angle to this as well. The cosmological principle is not just a statement about the universe, it's a statement about our place in it. The principle says that we are not special. Our location in space is not unique. If you traveled to another galaxy a billion light-years away, the universe would look roughly the same. No preferred location, no center, no edge. This idea, sometimes called the Copernican principle, has been a guiding assumption in cosmology since the early 20th century. It's the reason we trust that the laws of physics are the same everywhere, that the observations we make from Earth apply to the entire cosmos. If the HCBGW is real, it doesn't overturn the Copernican principle directly. It's not saying we're at the center of some special structure. But it does suggest that the universe is lumpier, more varied, more heterogeneous at large scales than the cosmological principle assumes. It opens the door to the possibility that there are regions of the universe with properties significantly different from our local neighborhood. Maybe some regions are more conducive to galaxy formation. Maybe some have different expansion rates due to local variations in dark energy. Maybe the universe is not as uniform as we've been assuming, and the smoothness we see in the cosmic microwave background is a starting condition that has since diverged into a more complex, more structured cosmos. That idea is unsettling because it makes the universe harder to model. A homogeneous universe is simple. You can write down equations that describe the whole thing with a handful of parameters. A heterogeneous universe is complicated. You need more parameters, more assumptions, more details about local conditions. The predictions become less precise. The models become harder to test. It's not impossible to work with, but it's messier. And cosmologists, like most scientists, prefer clean answers. There's also a historical echo here. In the 1920s and 30s, when Edwin Hubble and others first mapped the distribution of galaxies, they noticed that galaxies weren't evenly spread. They clustered. Some regions of the sky had many galaxies, others had few. For a while, some astronomers worried that this clustering violated the cosmological principle. Maybe the universe wasn't homogeneous. Maybe there were large-scale structures that shouldn't exist. Then, as surveys improved and more galaxies were catalogued, the picture became clearer. The clustering was real, but it averaged out at larger scales. The universe had structure, filaments and clusters and voids, but those structures were superimposed on a smooth background. The cosmological principle survived. The universe was lumpy at small scales, smooth at large scales. Problem solved. The HCBGW feels like a repeat of that debate, but at a higher level. Once again, we've found a structure that seems too large. Once again, some astronomers are questioning whether the cosmological principle holds, and once again the resolution will come from better data and more detailed modelling. Either the structure will turn out to be a projection effect or an artifact, and the principle will hold, or the structure will turn out to be real, and we'll have to adjust our understanding of how the universe is put together. The stakes are not small. If the cosmological principle fails, it doesn't just affect one corner of astrophysics, it affects everything. The age of the universe, the distance scale, the expansion rate, the formation history of galaxies, the distribution of dark matter, the nature of dark energy. Every calculation in cosmology assumes that the universe is, on average, the same everywhere. Drop that assumption and you're rebuilding the foundation while the building is still standing. But let's be clear about what we're actually claiming here. The Hercules-Corona Borealis Great Wall is not a confirmed structure. It's a claimed structure, inferred from a sparse sample of gamma-ray bursts in a limited region of the sky. The statistical significance is high enough to take seriously, but not high enough to rule out chance or systematic error. The size estimates vary depending on the method, and the interpretation depends on assumptions about how gamma-ray bursts trace the underlying galaxy distribution. It is entirely possible that in 10 years, with better data, the HCBGW will be remembered as a cautionary tale about overinterpreting incomplete surveys, or it's possible it will be remembered as the first hint that the universe is stranger than we thought. What we do know is that the universe keeps surprising us. Every time we build a better telescope, survey a larger volume, or look at a different wavelength, we find something we didn't predict. Structures that are bigger, older, more massive, or more organised than the model said they should be. Some of those surprises fit into the existing framework with minor adjustments. Others force us to rethink the framework itself. The HCBGW is in that second category. If it's real, it's not a minor adjustment. It's a challenge to one of the core principles of cosmology. And here's the thing, we can't just dismiss it. We can't just say, that's impossible, so it must be wrong. Science doesn't work that way. If the data point towards something, even something uncomfortable, we have to follow the data. We have to test it, refine it, look for alternative explanations, and see whether the result holds up under scrutiny. That process takes time. It takes more observations, more surveys, more gamma-ray bursts, more galaxy redshifts, more everything. The HCBGW was first reported in 2014. It's been a decade and we still don't have a definitive answer. That's not a failure, that's science. The big questions take time. What's clear is that the universe at the larger scales is less well understood than we'd like to admit. We've mapped superclusters like Laniakea and Shapley. We've traced the cosmic web across hundreds of millions of light years. We've measured the expansion rate, the age, the composition, the geometry. But when we push out to distances of 10 billion light years, when we try to map structures at the edge of the observable universe, the picture gets fuzzy. The data are sparse, the uncertainties grow, and occasionally something appears in that fuzzy picture that doesn't fit. Something that forces us to ask whether the rules we've been using are actually complete, or just the best approximation we have with the tools available. The Hercules-Corona Borealis Great Wall is that something. It's the structure that sits at the edge of the map, where the observations end and the speculation begins. Whether it's real or not, it's a reminder that the universe is under no obligation to make sense to us. It's a reminder that the map is not the territory, and the territory is vast, ancient, and full of features we're only beginning to decode. But there's a limit to how far we can see, a hard boundary beyond which no amount of better telescopes or longer observations will ever let us look. That boundary is not set by technology. It's set by physics, by the speed of light and the age of the universe. And understanding that boundary, understanding what it means to live inside an observable universe with edges, is the next step. Because the HCBGW, if it's real, is close to that edge. It's one of the most distant, most extreme structures we've ever detected. Push much farther, and we're not mapping the universe anymore. We're mapping the limits of what can ever be known. That's where we're going next. To the boundary, to the horizon, to the edge of everything we can see, and the vast unknown that lies beyond it. We just spent considerable time staring at a structure that might not exist. A wall of galaxies 10 billion light-years long, inferred from a handful of gamma-ray bursts, sitting right at the edge of what our models say is possible. If it's real, it breaks the rules. If it's not, it's a reminder that sparse data and wishful thinking can sometimes look like a discovery. Either way, the Hercules-Corona Borealis Great Wall is about as far out as we can reach. Not because our telescopes aren't good enough, though they could always be better, but because there's a limit, a hard boundary beyond which no telescope, no matter how powerful, will ever let us see. That boundary is not a wall in space. It's not a surface you could touch, or a barrier you could cross. It's a horizon, an edge to observation itself set by physics, by the speed of light, and by the age of the universe. We call it the Observable Universe, and it's exactly what the name suggests. The region of space from which light has had time to reach us since the beginning of everything. The observable universe has a size, roughly 93 billion light-years across. That's the diameter. The radius, the distance from here to the farthest point we could theoretically see, is about 46 to 46.5 billion light-years, depending on whose estimate you trust, and how you account for the uncertainties in the expansion rate. 93 billion light-years sounds impossibly large, and it is. But it's also smaller than you might expect, because the observable universe is not the universe. It's just the part we can see, the part whose light has had time to travel to us. Beyond that edge, the universe keeps going. How far, we don't know. Maybe it goes on forever. Maybe it loops back on itself. Maybe it ends at some unimaginable distance in a way we have no framework to describe. We can't see that far, so we can't say. All we know is that there's more, and we'll never be able to look at it. Let's start with why the limit exists, because it's not obvious until you think through the mechanics. Light travels fast, roughly 300,000 kilometers per second. In 1 year, light covers about 9.5 trillion kilometers, a distance we call a light year. The universe is about 13.8 billion years old, so light has been traveling for 13.8 billion years. You'd think, reasonably, that the observable universe should have a radius of 13.8 billion light-years. The light from the farthest objects has been travelling since the beginning, so it should have covered 13.8 billion light-years by now. Simple, except the universe has been expanding the entire time. Space itself is stretching. And when light travels through expanding space, the rules get strange. The light still moves at the speed of light relative to the space around it, but the space is moving too, expanding, pulling the starting point and the end point farther apart even as the light is trying to cross the gap. The result is that a photon can travel for 13.8 billion years and cover far more than 13.8 billion light-years of distance. Not because the photon sped up, because the finish line kept moving while the race was happening. Here's a better way to think about it. Imagine you're on a moving walkway at an airport, the kind that carries you forward while you walk. Now imagine the walkway is stretching as you walk on it. Every step you take, the walkway gets a little longer. You're still walking at the same speed, but the distance you've covered keeps growing because the surface beneath you is expanding. By the time you reach the end, you've travelled farther than you walked. That's what happens to light in an expanding universe. The photon moves at the speed of light, but the space it's moving through is stretching, so by the time it arrives, the place it started is much farther away than it was when the photon began its journey. Run the numbers, account for the expansion, and you get a radius of about 46 billion light-years. That's the moving distance, the distance accounting for how much space has expanded since the photon was emitted. The object that emitted the light we're seeing today was much closer when the light left, but by now, 13.8 billion years later, it's 46 billion light-years away. We're looking at where it was, not where it is. And where it is now is so far away that even if it sent a new photon toward us at this exact moment, that photon would never arrive. The space between us and that object is expanding faster than light can cross it. That's the edge. Not a place you could visit, but a boundary in time. A horizon beyond which events that are happening right now will never be visible to us, no matter how long we wait. The universe beyond that horizon is not gone, it's just disconnected, causally separated. We can't see it, we can't signal it, and nothing that happens there can ever affect us. It might as well be a different universe. So the observable universe is a sphere centered on Earth, or more accurately, centered on wherever you happen to be, because the boundary is observer dependent. If you travel to a galaxy 10 billion light-years away, your observable universe would be a sphere centered on that galaxy. Some of the objects you'd see would be different from the ones we see from here. Some of the objects we see would be beyond your horizon. The observable universe is not a fixed structure, it's a perspective. A bubble of space defined by how much time has passed since the Big Bang, and how far light has been able to travel in that time. And the bubble is growing. Every year, light from slightly more distant regions reaches us for the first time. The observable universe expands by roughly 1 light-year per year in radius. That sounds like a lot. It's not. At the scale we're talking about, 1 light-year per year is glacial. But it does mean that over time, more of the universe becomes visible. Galaxies that were once beyond the horizon drift into view as their light finally completes the journey. Not because they're moving toward us, because the light they emitted billions of years ago is just now arriving. There's a catch though. The expansion of the universe is accelerating. Driven by dark energy, the mysterious force that makes up about 70% of the universe's total energy budget, the rate at which space is stretching is increasing over time. That acceleration has a consequence. Galaxies that are currently within our observable horizon will eventually cross back out of it, not because they're moving away faster than light, which they're not, but because the space between us and them is expanding so fast that their light will stop being able to reach us. In the far future, trillions of years from now, most of the galaxies we can see today will have receded beyond the horizon. The observable universe will shrink. Our descendants, if any exist, will look out at a much emptier sky. A universe dominated by our local group of galaxies, everything else gone, lost to the expansion, invisible forever. But we're not there yet. Right now, the observable universe is full. Galaxies in every direction, stretching back to the edge of time. And at that edge, the farthest we can currently see, there's a glow. A faint uniform background of microwave radiation that fills the entire sky. We call it the cosmic microwave background, or CMB, and it's the closest thing we have to a visible edge. The cosmic microwave background is not the edge of the universe, it's the edge of what we can observe using light. It's the oldest light in the universe, emitted when the cosmos was about 380,000 years old. Before that moment, the universe was too hot and dense for light to travel freely. Protons and electrons were zipping around as a hot plasma, and photons couldn't get more than a short distance before scattering off a charged particle. The universe was opaque, a glowing fog. Then, about 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, the photons had nothing to scatter off of. They stopped bouncing around and started travelling in straight lines. The universe became transparent. Those photons have been travelling ever since, stretched by the expansion of space from high-energy visible and ultraviolet light into low-energy microwaves. That stretched light is the cosmic microwave background. It's a snapshot of the universe at the moment it became transparent, a baby picture of the cosmos, and it's the farthest back in time we can see using electromagnetic radiation. We detect the CMB today as a faint glow with a temperature of about 2.7 degrees above absolute zero. It's the same in every direction, smooth to an extraordinary degree, with temperature variations of only about 1 part in 100,000. Those tiny variations, the hot spots and cold spots, are the density fluctuations that eventually grew into galaxies, clusters, and the cosmic web. The CMB is a map of the seeds of structure, the initial conditions that set everything in motion. But the CMB is also a wall. Beyond it, we can't see using light because there was no free-travelling light to see. The universe before 380,000 years was opaque. If you want to probe earlier times, you need something other than photons. Neutrinos, maybe, which interact so weakly with matter that they would have escaped the early plasma and travelled freely. Or gravitational waves, ripples in space-time itself, which also pass through matter without scattering. Astronomers are working on detecting those signals, building gravitational wave observatories and neutrino detectors, but for now, the CMB is the limit. It's the edge of the observable universe as seen through the lens of light. The CMB sits at a redshift of about 1090. Redshift is the measure of how much the universe has expanded since the light was emitted. A redshift of 1090 means the universe has expanded by a factor of 1096 since the CMB photons started their journey. The wavelength of those photons has stretched by the same factor. What started as high-energy ultraviolet light is now low-energy microwaves, and the place those photons came from, the surface of last scattering, the shell of hot plasma that emitted them, was about 42 million light-years away from our location when the light was emitted. But by now, accounting for the expansion, that surface is about 46 billion light-years away. It's the edge of the observable universe. If you could somehow see the CMB with your eyes, which you can't because your eyes don't detect microwaves, it would look like a glowing shell surrounding you in every direction, a perfect sphere. And everywhere you looked on that sphere, you'd be seeing the universe as it was 380,000 years after the Big Bang. Same age, same temperature, same density. The entire observable universe, at its farthest edge, is frozen in time at that single moment. Now here's the strange part. The CMB is not a physical object sitting out there at a fixed distance. It's a light cone boundary. The photons we see today as the CMB were emitted from a shell of space that was about 42 million light-years away from us at the time. But those photons have been travelling toward us for 13.8 billion years, and during that time, the space they came from has been expanding, carrying that shell of plasma farther and farther away. By now, the matter that emitted the CMB photons we're seeing today is no longer a hot plasma. It's cooled, it's condensed into gas, formed stars, assembled into galaxies. Some of those galaxies might be nearby, some might be in our local supercluster. The matter that emitted the CMB we see in one direction is not the same matter that emitted the CMB we see in the opposite direction. They're completely different regions of space, now separated by the full width of the observable universe. And here's the uncomfortable part. If there's a galaxy sitting at the location that emitted the CMB photons we're detecting right now, and if someone in that galaxy is looking back at us, they're not seeing us. They're seeing the CMB photons emitted from our location 13.8 billion years ago, when our region of space was also a hot plasma. We are their CMB. They are ours. The boundary is symmetrical. Every observer in the universe sees themselves at the centre of an observable sphere, surrounded by a CMB shell marking the edge of what they can see. This is the part that breaks most people's intuition. The observable universe is not a thing that exists independently of the observer. It's a perspective, a region defined by your location and the age of the universe. Move to a different galaxy, and your observable universe shifts. Some of the things you see from here disappear beyond the horizon. Some of the things beyond our horizon come into view. There is no universal map, no single correct picture. Every observer has their own bubble, their own edge, their own CMB shell, and none of them are wrong. They're all correct descriptions of what's observable from that location. So what lies beyond the edge? What's out there in the unobservable universe? Nobody knows. And that's not because we haven't looked hard enough or because our instruments aren't good enough. It's because, by definition, the unobservable universe is unobservable. Light from those regions hasn't reached us yet. Maybe it will in the future as the observable universe continues to grow. Maybe it won't because the expansion is too fast and the light will never close the gap. Either way, right now, we can't see it. We can't measure it. We can't confirm or deny anything about what's there, but we can guess. And the guesses fall into a few broad categories. The simplest guess is that the unobservable universe looks more or less like the observable universe. Same kinds of galaxies, same distribution of matter, same cosmic web of filaments and voids. This is what the cosmological principle predicts. The universe is homogeneous and isotropic on large scales, which means if you travel to a region currently beyond our horizon, you'd see roughly the same thing we see here. No dramatic changes, no exotic structures, just more galaxies, more clusters, more superclusters, stretching on indefinitely, maybe forever. The observable universe would be a representative sample of the whole. This guess is supported by the smoothness of the cosmic microwave background. The CMB is almost perfectly uniform across the entire sky, which suggests that the conditions in the early universe were the same everywhere, at least within the regions we can observe. If the universe was uniform at 380,000 years old, it's reasonable to think it's still uniform now, just scaled up by billions of years of expansion and structure formation. Extrapolate outward, and you'd expect the unobservable universe to look like more of the same, but there are exceptions. Some cosmological models predict that the universe could have different properties in different regions. Inflation, the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang, allows for the possibility that different regions inflated by different amounts, or stopped inflating at different times, or started with slightly different initial conditions. If that happened, the unobservable universe could include regions with different densities, different expansion rates, or even different physical constants. Maybe the strength of gravity is different there. Maybe the masses of fundamental particles are different. Maybe the laws of physics themselves vary from place to place. This idea is speculative, and most physicists are uncomfortable with it because it's untestable. If the laws of physics vary in regions we can never observe, we can't confirm it, which means it's not clear the idea qualifies as science in the usual sense. But it's allowed by the models. Inflation predicts a universe much larger than the observable part, possibly infinite, and in an infinite universe, anything that can happen will happen somewhere. That includes regions with conditions wildly different from ours. There's another possibility, even stranger. Some versions of inflation predict that the universe is not just larger than what we can see, but infinitely larger. And in an infinite universe, the same configurations of matter will repeat. Not because there's a pattern or a design, but because there are only so many ways to arrange a finite number of particles in a finite volume. If space goes on forever, and matter is distributed more or less uniformly at the larger scales, then eventually you'll find another region that looks exactly like ours. Same galaxies, same stars, same planets, same you sitting in the same chair reading the same words. An exact duplicate. Not a copy in the sense that someone built it, a duplicate in the sense that the same random arrangement happened again, somewhere out there in the infinite expanse. How far away would that duplicate be? The estimates are absurd. Something like 10 to the power of 10 to the power of 115 meters. A number so large it doesn't fit in any normal notation. The observable universe is about 10 to the power 27 meters across. The distance to a duplicate observable universe would be incomprehensibly, unimaginably larger. You couldn't travel there, you couldn't signal it, you couldn't confirm it exists. It's a consequence of assuming the universe is infinite and uniform, but it's not a consequence you can test. Most cosmologists treat this as a curiosity rather than a serious prediction. Interesting to think about, but not something that changes how we do astronomy. The observable universe is plenty large enough to keep us busy. The stuff beyond the edge, whether it's more of the same or something completely different, doesn't affect our measurements or our models. We can only work with what we can see, and what we can see is limited not just by distance, but by time. The observable universe is a time machine. The farther away we look, the further back in time we see. Look at a galaxy a billion light years away, and you're seeing it as it was a billion years ago. Look at the CMB, and you're seeing the universe as it was 13.8 billion years ago, minus 380,000 years. We can't see the universe as it is now at this moment, because the light from now hasn't had time to reach us. We're always looking at the past. This has strange consequences. The galaxies we see at the edge of the observable universe, the ones whose light has been travelling for more than 13 billion years, don't look like that anymore. They've aged, they've evolved, they've merged with other galaxies, formed new stars, maybe been torn apart by gravitational interactions. By now, those galaxies are 46 billion light-years away, and if we could somehow see them as they are today, they'd look completely different. But we can't. We're stuck seeing them as they were, and they're stuck seeing us, if anyone's there to look, as we were billions of years ago, when our region of space was still assembling its first stars. The speed of light is the ultimate speed limit, and it's also the ultimate delay. Every observation we make is out of date. The sun we see is 8 minutes old. The nearest star is 4 years old. Andromeda is 2.5 million years old. The most distant galaxies are more than 13 billion years old. We live in a universe where the present is invisible. All we have is the past, layered and stacked at different distances, each layer representing a different moment in cosmic history. And the farther back we look, the younger and stranger the universe becomes. Galaxies near the edge of the observable universe are smaller, bluer, more chaotic. They're still forming, still merging, still figuring out how to be galaxies. The stars are younger, hotter, more massive. The elements heavier than hydrogen and helium are rarer because fewer generations of stars have lived and died. The cosmic web is less developed, the filaments thinner, the voids smaller. It's a rougher, more violent universe, closer to the starting conditions, not yet settled into the structures we see nearby. Push all the way back to the CMB, and you're looking at a universe with no stars, no galaxies, no planets. Just hot plasma cooling in the dark, a few 100,000 years earlier, and the plasma would be even hotter, dense enough to glow like the surface of a star. Go back to the first second, and you're in a realm where protons and neutrons haven't even formed yet. Just quarks and gluons in a soup so hot that the rules of particle physics start to blur. And if you could somehow go back to the very first moments, fractions of a second after the Big Bang, you'd be in a regime where space and time themselves might not have existed in any recognizable form. Quantum fluctuations, inflation, a singularity where the equations break and the concept of before stops meaning anything. We can't see that far, not with light, not with anything. The observable universe has a floor as well as an edge, a boundary in time beyond which our tools stop working. The CMB is the floor. Earlier than that, we're guessing, using models, running simulations, testing hypotheses against indirect evidence. But we're not observing, we're inferring, and the further back you go, the weaker the inferences become. So here's where we are. We live inside a bubble. 93 billion light-years across, expanding at 1 light-year per year, filled with 2 trillion galaxies, give or take, each containing billions or trillions of stars, structured into filaments, clusters, superclusters, walls, and voids. All of it built over 13.8 billion years from tiny density fluctuations imprinted in the first moments after the Big Bang. And surrounding the whole thing, at the farthest edge we can see, a glowing shell of microwave radiation marking the moment the universe became transparent. Beyond that shell, the universe continues. How far? We don't know. What it looks like? We can't say. Whether it's the same as what we see here or completely different, we have no way to check. The unobservable universe is by definition beyond reach. Not because our technology is limited, though it is, but because the structure of space-time itself prevents us from seeing it. Light has only had so much time to travel, and space has been expanding the whole time, and the combination of those two facts sets a boundary we can't cross. And that boundary is not fixed, it's moving, growing. Every year a little more of the universe becomes observable. But at the same time, other parts are slipping away, pushed beyond the horizon by the accelerating expansion. In the long run, the observable universe will shrink. Most of the galaxies we see today will eventually disappear from view, their light redshifted into invisibility, their signals stretched and weakened until they fade entirely. Future civilizations, if any exist, will look out at a lonelier cosmos. Fewer galaxies, darker skies, a universe that looks smaller and emptier than the one we see now, even though the actual universe will be just as large, just as full. It's just that most of it will be beyond their horizon. We're living in a relatively good time for observational cosmology. The universe is old enough that galaxies have formed and structure has developed, but young enough that most of those galaxies are still within our observable horizon. We can see the cosmic web, we can map superclusters, we can detect the CMB, we can trace the history of the universe from the first few 100 million years all the way to the present. In a few trillion years, that won't be possible. The data will be gone, lost to the expansion, and future astronomers will have a much harder time figuring out the history of the cosmos. They'll be stuck inside a smaller bubble with fewer clues. But that's a problem for them. Right now, we have the data. We have the maps. We have the observations stretching from our local neighbourhood all the way to the edge of time. And what those observations show is a universe far larger, far older, and far more complex than anyone imagined even a century ago. A universe where the Milky Way is one galaxy among trillions, where our supercluster is one node in a web stretching billions of light years, where structures like the Hercules-Corona Borealis Great Wall, real or not, push up against the limits of what the models allow. And all of it, every galaxy, every star, every photon we detect is just a tiny fraction of the whole. The observable universe is not the universe, it's the part we can see, the part whose light has reached us, the part we can measure and map and argue about. Beyond that, there's more, maybe infinitely more. And we'll never know for sure because the boundary is set by physics, by the speed of light, and the age of the universe and the relentless expansion of space. That boundary has consequences, not just for astronomy, but for philosophy, for how we think about our place in the cosmos, for what it means to live in a universe so large that most of it is permanently hidden from view. A universe where the things we can observe are a small, perhaps unrepresentative, sample of the whole, where the answers to the biggest questions, what's beyond the edge, how large is the full universe, are we typical or unusual, might be forever out of reach. Those are not just scientific questions, they're existential ones, and they don't have comfortable answers. Because the universe we can see is already larger than our minds can hold, and the universe beyond that is larger still. And somewhere in all that immensity, on a small rocky planet orbiting an average star in an unremarkable galaxy, a species of primates has figured out how to measure the size of the observable cosmos and realised that it's not enough, that the map has edges, that there are things we'll never see, questions we'll never answer, distances we'll never cross. Living with that knowledge changes something. It shifts the way you think about scale, about significance, about what matters and what doesn't. Because if the observable universe is just a bubble, and the full universe is unimaginably larger, then everything we've ever known, every person who's ever lived, every thought and action and empire and war, has happened inside a region of space so small compared to the whole that calling it insignificant is almost generous. And yet, here we are, thinking about it, measuring it, trying to make sense of it. That tension between the enormity of the universe and the smallness of our place in it is where we're going next. Not to resolve it, because it can't be resolved, but to sit with it, to think through what it means to be a conscious thing in a universe this large, to ask whether size matters, whether perspective matters, whether anything we do has significance when measured against the scale of the cosmos. Those are the questions that follow naturally from understanding the limits of vision, from realising that the map ends but the territory keeps going, that we live inside a bubble and the bubble is all we'll ever have. So let's talk about what that does to our sense of reality, about how scale reshapes meaning, about what it's like to be human in a universe that's so much larger than us that it makes the word large feel like a joke. We just finished mapping the edges, the boundary of the observable universe, a sphere 93 billion light-years across, marked at its farthest reach by the faint glow of the cosmic microwave background. A horizon set by physics, by the speed of light, and the age of the universe beyond which we cannot see and never will. We talked about what lies past that edge, the unobservable universe stretching on in directions and distances we can only guess at. Maybe it looks like what we see here. Maybe it's completely different. Maybe it goes on forever. We don't know, and the not knowing is built into the structure of space-time itself. But here's the thing about edges. Once you find one, once you realise there's a limit to what you can see, the question stops being about what's out there and starts being about what it means that we're asking in the first place. A species that lives for maybe 80 years on a planet 8,000 miles wide has figured out how to measure structures 10 billion light-years long. A collection of organised matter, carbon and water and electrical impulses, has looked at the night sky and worked backward to the moment 380,000 years after the universe began. We've mapped our location inside a supercluster 520 million light-years across. We've traced the motions of galaxies being pulled toward a gravitational centre 200 million light-years away. We've found black holes weighing 66 billion times the mass of our Sun and galaxies containing 100 trillion stars, and every single one of those discoveries makes us smaller. That's the paradox. The more we learn about the universe, the more we understand about the scale and structure of reality, the more obvious it becomes that we are not the point. Not the centre, not the purpose, not even a significant feature. We're a detail, a footnote, a brief arrangement of atoms on a small planet orbiting an unremarkable star in a galaxy that's one of 2 trillion, inside an observable universe that's itself just a bubble in something unimaginably larger. Every measurement we make, every structure we find, every distance we calculate drives that point home. We are not important at the scale of the cosmos, we barely register. And yet we keep looking, we keep measuring, we keep building bigger telescopes, better instruments, more sensitive detectors. We keep asking questions we know might not have answers. Why? What drives a species this small to care about things this large? What does it mean to spend lifetimes trying to understand a universe that, by every objective measure, does not care whether we understand it or not? That's what this chapter is about. Not the structures themselves, but what they do to us. What it means, psychologically and philosophically, to be the kind of thing that can comprehend its own insignificance. To stand on a rock 8,000 miles wide and know, really know, that the rock is one planet among trillions, in a galaxy among trillions, in a universe so large that calling it large is an insult to the word, and to keep asking questions anyway. Let's start with the most immediate effect, the humbling. Because that's the word everyone uses when they talk about cosmology, and it's the right word, but it doesn't quite capture the full weight of what's happening. Humbling suggests being reminded that you're not as important as you thought. That's part of it, but it's deeper than that. It's not just that we're small, it's that we're so small that the difference between us and nothing is a rounding error. Here's a way to think about it. The observable universe contains about 2 trillion galaxies. Each galaxy contains, on average, somewhere between 100 billion and a few 100 billion stars. Let's be conservative and say 100 billion. That gives us 2 times 10 to the 23rd stars, 200 billion trillion stars. Each star is a sun. Each sun potentially has planets. Some of those planets are rocky, some are in the habitable zone. Some, statistically, must have developed life at some point in their histories. The numbers are so large that even if life is rare, even if the odds are 1 in a billion, you still end up with hundreds of billions of planets where something has crawled out of the ocean, or figured out how to photosynthesize or built a civilization. Now zoom out. Our sun is one of those 200 billion trillion stars. Earth is one planet among trillions upon trillions. Humanity, all of us, every person who has ever lived, every thought anyone has ever had, every empire and war and discovery and work of art, all of it has happened on this one planet, in one solar system, in one galaxy, during a span of time that's less than 1,000% of the universe's total age. We've been here for a few 100,000 years. The universe has been here for 13.8 billion. We're not even a blip. We're a blip's shadow. And it gets worse, because even on Earth, even in the narrow window of time we've existed, most of what humans have ever done is already forgotten. How many people lived in the year 1000? Millions? Tens of millions? How many of their names do you know? How many of their thoughts survived? A handful? A tiny fraction. The rest are gone, not just dead, but erased. No records, no memory, no trace. And that's on our own planet, in our own species, within recorded history. Zoom out to the scale of galaxies, and we're not even a blip's shadow. We're a quantum fluctuation, a momentary arrangement of particles that happen to be self-aware for a few thousand years before dissolving back into the background noise. That's humbling. But it's also more than humbling, it's destabilizing, because humans are not built to think at that scale. We're built to think about things we can see, touch, affect. The people in our tribe, the food we need to find today, the shelter we need to build before winter. Our brains evolved to solve problems at human scales, over human time scales, and they're very good at it. But they're not good at holding the idea of 2 trillion galaxies. They're not good at processing 10 billion light years. Those numbers don't connect to anything in lived experience. They're abstractions. Symbols on a page, you can write them down, you can do the math, but you can't feel them the way you feel the weight of a rock in your hand. So what happens when you force yourself to think about them anyway? When you sit with the numbers long enough that they start to mean something? For most people, the answer is a kind of vertigo, a sense that the ground has shifted and you're not standing where you thought you were. Everything you assumed was solid turns out to be provisional. The things that felt important, your job, your relationships, your problems, start to look trivial when set against the backdrop of a universe that's been running for 13.8 billion years and will keep running for trillions more. You start to ask uncomfortable questions. If nothing we do matters at the scale of the cosmos, does anything we do matter at all? If the universe doesn't care whether we exist, why should we care about anything? That's not a new question. Philosophers have been asking it for thousands of years. But cosmology makes it sharper. Because for most of human history, we could tell ourselves a story where we mattered. We were at the center of creation. The Earth was the center of the universe. The sun and stars revolved around us. God made the world for us, we were the point. That story held for a long time. It was comforting. It gave life meaning, purpose. Then Copernicus came along and said, actually the Earth orbits the sun. We're not at the center. Galileo confirmed it with a telescope. Suddenly we were just another planet. That was hard to accept. The Catholic Church fought it. People resisted. It felt like a demotion. But eventually the evidence was overwhelming. Fine. We're not at the center of the solar system. But maybe we're still special. Maybe the solar system is at the center of the universe. Then, in the early 1900s, astronomers figured out that the Milky Way is a galaxy, and the fuzzy nebulae scattered across the sky are other galaxies, millions of light years away. The universe was suddenly much larger, and we weren't at the center of it. We were in a spiral arm of one galaxy among billions, another demotion. But maybe, people said, maybe the Milky Way is still near the center of all those galaxies. Maybe there's still a preferred location. Then Edwin Hubble discovered that the universe is expanding. Galaxies are moving away from each other in all directions. There is no center. Or rather, every point is the center from its own perspective. We're not special. We're typical. The cosmological principle says the universe looks the same everywhere, which means our location is no more or less important than any other location. We're not at the center because there is no center. Final demotion. We've gone from the focal point of creation to an arbitrary coordinate in an expanding cosmos. And every step of that process has been fought. Not because the science was bad, but because the implications were uncomfortable. Humans want to matter. We want to believe that our existence has significance, that the universe cares, that we're here for a reason. Cosmology keeps saying, no, you're not special. You're a product of physics and chemistry, the same physics and chemistry that makes stars and rocks and gas clouds. You're made of atoms that were forged in dying stars billions of years ago, scattered into space, swept up into a new solar system, and briefly organized into a pattern that looks around and asks why. There's no purpose, no design, just time and probability. That's the anthropocentric view being dismantled. Anthropocentric means human-centered, the assumption that we're the main event. Every discovery in cosmology for the past 500 years has been a correction to that assumption. We're not at the center. We're not unique. We're not the reason the universe exists. We're a consequence, an emergent property, a thing that happened, not a thing that was meant to happen. And here's the hardest part. Even knowing that, even accepting it intellectually, it doesn't change how life feels from the inside. You still wake up in the morning, you still have problems, you still care about the people around you, the work you're doing, the future you're trying to build. None of that goes away just because you've learned that the universe is 93 billion light years wide and you're a speck inside it. The scale doesn't erase the experience, it just reframes it. So you're left with two perspectives that don't reconcile. From the cosmic perspective, you're nothing, irrelevant. A brief flicker of organized matter that will dissolve back into chaos in a few decades. From the human perspective, you're everything. The only perspective you'll ever have. The only life you'll ever live. Both perspectives are true. and they contradict each other, and you have to live with that contradiction because there's no way to resolve it. Some people respond to this by doubling down on the cosmic perspective. They say, fine, nothing matters, so I'm free. No cosmic judge, no ultimate meaning, no pressure to be anything other than what I am. That's liberating in its own way. If the universe doesn't care, then the only meaning is the meaning you create, the relationships you build, the things you care about, the small acts of kindness or creation or curiosity that fill the time between birth and death. It's not meaning handed down from above, it's meaning you make. And maybe that's enough. Others respond by rejecting the cosmic perspective entirely. They say, I don't care how big the universe is. I care about my family, my community, my life. That's the scale that matters to me. And they're not wrong, because the cosmic scale is inhuman. It's not a scale we're built to operate at. Trying to live your life with constant awareness of 10 billion light years is paralyzing. You can't function that way, so you zoom back in, you focus on what's in front of you, you let the rest be background. And then there's a third group, smaller, that tries to hold both perspectives at once, to be aware of the scale, to sit with the discomfort of insignificance, and to keep asking questions anyway. Not because the questions have comfortable answers, but because asking is what we do. That's the cosmologist's position. That's the philosopher's position. And it's an uncomfortable place to stand because it doesn't offer resolution. It offers tension. The universe is vast and indifferent, and we're tiny and temporary, and somehow that makes the act of trying to understand it more meaningful, not less. Because the universe doesn't care, but we do. And that caring, that curiosity, is the only thing separating us from the rocks and gas clouds we're made of. Now let's talk about time, because the scale of space is only half the problem. The scale of time is the other half, and it's just as disorienting. We've been talking about distances, 10 billion light years, 93 billion light years, but every one of those distances is also a time. Light takes time to travel. When you look at something 10 billion light years away, you're not seeing it as it is now. You're seeing it as it was 10 billion years ago. The universe is a time machine. The farther you look, the further back you go. And the depths of time we're talking about are so extreme that they make human history look like a sneeze. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Life on Earth started about 3.8 billion years ago. For most of that time, life was single-celled. Multicellular life didn't show up until about 600 million years ago. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. Humans, anatomically modern humans, have been around for maybe 300,000 years. Recorded history goes back about 5,000 years. 5,000 years out of 13.8 billion. That's roughly 0.00036% of the universe's age. If the history of the universe were compressed into a single year, with the Big Bang happening at midnight on January 1st, humans would show up at about 11:58 p.m. on December the 31st. Recorded history would be the last few seconds before midnight. Your entire life would be a fraction of the last second, a blink. Cosmologists call this deep time. The idea that the universe operates on timescales so long that human experience is essentially instantaneous by comparison. Deep time is hard to grasp because our brains aren't built for it. We understand days, months, years, maybe decades if we're thinking about our own lifespans, but millions of years, billions, those numbers are too big. They lose meaning. Here's a way to make it slightly more concrete. Imagine 1 second represents 1 year. At that scale, your entire life is maybe 80 seconds, a long human lifetime. The entirety of recorded history, from the first Sumerian tablets to now, is about an hour and a half. The whole span of human existence, 300,000 years, is about 3.5 days. Dinosaurs lasted about 2.5 years. Life on Earth has been around for about 120 years. The Earth itself is 143 years old, and the universe, 437 years. At 1 second per year, the Big Bang happened in the late 1500s. Shakespeare was writing plays about 50 years after the universe began. That's deep time. And the structures we've been talking about, the superclusters and filaments and walls, were built over those timescales. Gravity works slowly. A galaxy doesn't form in 1 million years. It takes hundreds of millions, even billions. The cosmic web, the filaments connecting galaxy clusters across hundreds of millions of light years, took most of the universe's history to assemble. The Great Wall, if it's real, is a structure that started forming when the universe was only a few billion years old and has been growing ever since. It's older than our solar system, older than most of the stars you can see in the night sky. It was there long before we were, and it will be there long after we're gone. Deep time forces a perspective shift. It makes you realize that the universe doesn't run on human schedules. Stars take millions of years to form and billions of years to die. Galaxies merge over hundreds of millions of years. The expansion of space is so slow that it's invisible at human timescales, but over billions of years, it doubles the size of the universe. We're living in a single frame of a movie that's been running for 13.8 billion years and will keep running for trillions more. Everything we do, everything we've ever done, happens in that single frame. We're not even a scene, we're a flicker. And once you understand that, once you really sit with the idea that the universe has been here for billions of years and will be here for billions more, the things that feel urgent start to look less urgent. The problems that dominate your daily life, your job, your bills, your plans for next year, they're real and they matter to you. But they're happening inside a window of time so small that it's invisible at the cosmic scale. 100 years from now, no one will remember your name. 1,000 years from now, your species might not exist. 1 billion years from now, the sun will have expanded into a red giant and swallowed the Earth. All the arguments, all the empires, all the monuments gone, erased. The universe will keep running, and nothing we did will have left a trace. So does that mean nothing matters? That's the question deep time forces you to ask. If everything is temporary, if the universe will eventually erase all evidence that we are here, what's the point? The uncomfortable answer is that the universe doesn't provide a point. Meaning is not a feature of the cosmos, it's a feature of minds. Humans invented meaning because we needed it. We're a social species, we build narratives, we assign value, we decide what's important. And we do that because it helps us survive and cooperate and make sense of the chaos around us. But the meaning we create is local. It works at human scales, over human lifetimes, in human communities. It doesn't scale up to galaxies. It doesn't scale up to billions of years. Those scales are indifferent. The stars don't care, the voids don't care, the expansion of space doesn't care. But here's the thing. That indifference doesn't erase the meaning we create. It just places it in context. Yes, the universe is vast and old and will outlast us by unimaginable margins. Yes, nothing we do will matter at the scale of the cosmos, but that's not the scale we live at. We live at the scale of days and years and human relationships, and at that scale, things do matter. The kindness you show to another person matters to them. The work you do, if it's good work, matters to the people it affects. The curiosity you feel when you look up at the night sky matters to you. None of that significance is diminished by the fact that the universe is 93 billion light-years wide. If anything, it's sharpened. Because if the universe doesn't provide meaning, and we're the only ones who can, then the act of creating meaning becomes the most important thing we do. That's the paradox at the heart of cosmology. The more we learn about how insignificant we are, the more we're forced to confront the fact that significance is something we make, not something we find. And once you realize that, once you accept that meaning is local and temporary and entirely dependent on minds like ours, you're left with a choice. You can despair, or you can double down. You can say, nothing matters, so why bother? Or you can say, nothing matters except what we decide matters, so let's decide carefully. Most people, when they first encounter the scale of the universe, lean toward despair. It's the natural response. You feel small, you feel powerless, you feel like the things you care about are trivial compared to the vastness of space and time, and they are, in a sense. But trivial doesn't mean meaningless. A conversation with a friend is trivial compared to the formation of a galaxy. But it's not trivial to you or your friend. The birth of a child is trivial compared to the life cycle of a star. But it's not trivial to the parents. Trivial is a judgment that depends on scale, and humans don't live at the cosmic scale. We live at the human scale, and at that scale, the small things are the things that matter most. So where does that leave us? We've spent this chapter walking through the philosophical weight of scale. The humbling effect of realizing we're one species on one planet in one galaxy among trillions, the dismantling of anthropocentric assumptions, the long historical process of learning that we're not the center and never were, the vertigo of deep time, The realization that the universe has been here for billions of years and will be here for billions more, and we're a brief flicker in the middle. And the uncomfortable truth that meaning is something we create, not something the universe hands us. But there's another layer to this. Because even though we're small, even though we're temporary, even though the universe doesn't care, we've still managed to figure out how big it is. A species that's been around for a few 100,000 years has measured the age of the cosmos. We've traced the formation of structure from the cosmic microwave background to the present. We've calculated the mass of black holes billions of times heavier than our sun. We've mapped the large-scale structure of the universe across billions of light years. We've built instruments sensitive enough to detect photons that have been travelling for more than 13 billion years. And we're not done. We're building better telescopes, running more detailed simulations, asking harder questions. That says something. Not about the universe, which doesn't care, but about us, about what we are, about the fact that we're the kind of thing that looks at the night sky and asks how far it goes. That builds tools to measure distances we'll never travel. That spends lifetimes trying to understand things that have no practical impact on daily survival. We're not unique in the universe. The laws of physics are the same everywhere, and life probably exists in countless other places, but we're unusual, because most matter doesn't ask questions. Most matter just sits there obeying the rules, following the equations. We're matter that woke up, matter that's curious. Matter that built a civilization, developed language, invented mathematics, and pointed telescopes at the sky to figure out where it came from. And that curiosity, that drive to explore and understand, is not something the universe gave us. It's something we are. It's built into the structure of human cognition, maybe into the structure of any sufficiently complex mind. We explore because we're curious. We're curious because not knowing feels uncomfortable, and discomfort drives action. Every map we've ever drawn started with an edge, a boundary, where the known ended and the unknown began. And every time we found an edge, we asked what was beyond it. We sailed across oceans, we climbed mountains, we dug into the earth, we built rockets and went to the moon. And when we looked up and saw galaxies, we built telescopes powerful enough to measure them. The Hercules-Corona Borealis Great Wall, if it's real, is the edge of the current map. A structure so large it challenges the models. 10 billion light-years long. A feature that shouldn't exist according to the cosmological principle. And whether it's real or not, whether it turns out to be a coherent structure or a statistical artifact, the fact that we're debating it tells you something about where we are as a species. We've pushed the map far enough that we're finding things at the limit of what the models allow. We're testing the boundaries of the cosmological principle itself, asking whether the universe really is homogeneous at the largest scales, or whether there's more structure, more complexity than we thought. That's not just science, that's philosophy. Because the cosmological principle is not just a statement about the distribution of galaxies, it's a statement about the nature of reality. It says the universe is the same everywhere, that the laws of physics don't change from place to place, that our observations here are representative of the whole. If the principle holds, the universe is comprehensible. We can extrapolate from what we see to what we can't see. We can build models that work everywhere. But if the principle fails, if the universe is more heterogeneous than we thought, then our models are local. They describe our region of space, but they might not apply elsewhere. And that opens the door to a much stranger cosmos, one where different regions have different properties, where the laws themselves might vary, where the universe is less uniform and more chaotic than the elegant equations suggest. We don't know yet. The data are still coming in. But the question is on the table, and asking the question is what we do. That's the human drive to explore. Not because exploration solves problems or makes life easier, though sometimes it does, but because not knowing is intolerable. We're the species that looks at a horizon and wonders what's beyond it. And when we find out, we keep going. Because there's always another horizon, another edge, another boundary where the map ends and the unknown begins. And here's the strangest part. The more we learn, the more we realize how much we don't know. Every answer generates new questions. We figured out the Earth orbits the Sun, and that led to the question of how the solar system formed. We figured out galaxies exist, and that led to the question of how galaxies formed. We figured out the universe is expanding, and that led to the question of what's driving the expansion. We found dark matter, dark energy, black holes, the cosmic web, and every discovery opened up new areas of ignorance. The map keeps growing, but so does the boundary. The more we see, the more we realize we're not seeing. That's not a failure, that's the process. Knowledge is not a destination, it's a direction. You don't reach a point where you understand everything and stop. You reach a point where you understand enough to ask better questions, and then you keep going. Because the unknown is not an obstacle, it's the point. It's the reason we build telescopes and launch satellites and spend decades analysing data. Not to eliminate mystery, but to engage with it, to push the boundary a little farther and see what's on the other side. So what does all this mean for us here now, on this small planet orbiting an average star in an unremarkable galaxy? It means we're part of something larger, not in the sense that the universe has a plan for us, because it doesn't, but in the sense that we're connected to the whole. The atoms in your body were forged in stars that died billions of years ago. The oxygen you breathe was made in a supernova. The carbon in your cells was cooked in the core of a red giant. You're made of stardust. That's not a metaphor, that's literally true. The universe made stars, stars made heavy elements made planets, planets made life, life made you. You're the universe looking at itself. A temporary arrangement of matter that happens to be self-aware, and that awareness comes with a cost. You know you're small, you know you're temporary, you know the universe doesn't care, but it also comes with a gift. You get to ask why. You get to look at the night sky and wonder how far it goes. You get to measure 10 billion light years and feel the vertigo of realizing how much space there is. You get to sit with the discomfort of insignificance and choose what to do with it. Despair, maybe, or curiosity, or both. The structures we've been talking about, the Great Wall, the superclusters, the cosmic web, they're not just objects in space, they're challenges to perspective, invitations to think bigger, to stretch the mind past the limits of everyday experience, to hold two contradictory ideas at once. You're nothing, and you're everything. The universe is indifferent, and your life has meaning. The cosmos is vast and incomprehensible, and you're part of it. Living with that contradiction is what it means to be human in the age of cosmology. You can't unknow the scale, you can't pretend the universe is smaller than it is, but you also can't live at that scale. You have to zoom back in, focus on the human, the local, the temporary, and somehow hold both perspectives at once, the cosmic and the personal, the eternal and the fleeting, the map and the territory. That's the philosophical impact of scale. It doesn't give you answers, it gives you a framework for asking better questions, and it reminds you that the act of asking, the drive to explore and understand, is not something the universe requires, it's something you choose. And that choice, small and temporary and cosmically irrelevant as it is the only thing that makes any of this mean anything. So we've walked through the implications, the humbling, the demotion, the realization that we're not special, the weight of deep time, the vertigo of billions of years, the paradox of meaning in an indifferent universe, and the strange fact that despite all of it, we keep looking. Keep asking, keep pushing the map farther, but there's one more question left. The map has edges, we've found them. The observable universe ends at the cosmic microwave background, and beyond that, we can't see. The Hercules-Corona Borealis Great Wall, if it's real, sits close to that edge. A structure so large it tests the limits of what's possible. So what happens next? What do we do when we've mapped as far as we can see? What questions are left when the tools we have can't reach any farther? That's where we're going. To the edge of the known and the beginning of speculation. To the ideas and theories and wild guesses about what might lie beyond the horizon. To the future of cosmology and the uncomfortable possibility that some questions might not have answers. Not because we're not smart enough, but because the universe itself has boundaries. And maybe, just maybe, we've reached them. We just finished talking about what the scale of the universe does to the human mind. The philosophical weight of realizing you're a brief flicker of organized matter inside a cosmos so vast that calling it vast feels inadequate. The humbling, the vertigo, the tension between cosmic insignificance and local meaning. We talked about deep time, the billions of years that came before and the trillions that will come after, and how all of human history fits into the last fraction of the last second of the cosmic calendar. We talked about the paradox of being matter that woke up and started asking questions about its own origins, knowing full well that the universe doesn't care whether we find answers. But here's the thing about questions, they don't stop. Even when you've reached the edge of the map, even when you've measured as far as the tools allow, the questions keep coming. Because the edge is never really the end, it's just where you currently are. And every time we've thought we'd reached a boundary, every time we've assumed we'd figured out the full extent of something, the universe has turned around and shown us we were wrong. The Milky Way was the universe until we discovered it was one galaxy among billions. The observable universe was smooth until we mapped the cosmic web. The larger structures were supposed to be a few 100 million light-years across until we found the Sloan Great Wall at over 1 billion light-years, and now we're staring at a claimed structure 10 billion light-years long, the Hercules-Corona Borealis Great Wall, and asking whether it's real or whether we've hit the limit of what the data can tell us. Either way, the question is the same: what's next? What lies beyond the edge of what we can currently see? What structures are out there, too faint or too distant to detect with today's instruments, waiting to be found when the next generation of telescopes comes online? What new physics might be hiding in the gaps between observation and theory? And when we push the map as far as it can possibly go, when we've surveyed every galaxy within the observable horizon, what then? Where does cosmology go when there's nothing left to observe? This is the chapter where we stop looking back and start looking forward. Not to predict the future, because predictions in science have a terrible track record, but to sketch the shape of the questions that haven't been answered yet, the mysteries that remain, the tools being built to tackle them, and the uncomfortable possibility that some of those mysteries might be permanent, not because we're not smart enough to solve them, but because the universe itself has placed limits on what can be known. Let's start with the obvious question. If the Hercules-Corona Borealis Great Wall is real, and it's 10 billion light-years long, could there be something even larger? Something we haven't found yet because it's farther away, or fainter, or oriented in a way that makes it hard to detect? The short answer is maybe. The longer answer is that it depends on whether the cosmological principle holds. The cosmological principle, remember, says the universe is homogeneous and isotropic on the larger scales, smooth when you average over large enough volumes. No giant walls or supervoids that dominate the structure. Structures larger than about 1.2 billion light-years shouldn't exist, because gravity hasn't had enough time to pull matter together across distances that large. The Hercules-Corona Borealis Great Wall, at 10 billion light-years, is already pushing that limit to the breaking point. If something larger exists, it's not just an outlier. It's evidence that the principle itself is incomplete. But let's be clear about what we're looking for. A structure larger than the Great Wall would have to be truly colossal. 15 billion light-years, 20 billion. At some point you're talking about features that span a significant fraction of the observable universe, which is 93 billion light-years across. A structure 20 billion light-years long would stretch across more than 20% of everything we can see. That's not just a wall, that's a fundamental organizing feature of the cosmos. If something that large exists, it changes the entire picture of how the universe is put together. And here's the uncomfortable part. We might not be able to detect it. Not because our telescopes aren't good enough, though they could always be better, but because structures that large would be made of galaxies so distant that their light has been stretched into the infrared or even the microwave spectrum. Detecting them requires instruments sensitive to those wavelengths, and it requires surveys that cover large fractions of the sky with enough depth to pick up faint distant objects. We're building those instruments. The James Webb Space Telescope is already online, and it's finding galaxies at the edge of the observable universe that are brighter and more massive than the models predicted. Euclid, a European Space Agency mission launched in 2023, is designed specifically to map large-scale structure across billions of light-years. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Webb's, allowing it to survey vast regions of the sky in unprecedented detail. Those three instruments together, Webb, Euclid, and Roman, are going to rewrite the map. They're designed to complement each other, covering different wavelengths and different survey strategies, and their combined data will give us the most detailed picture of large-scale structure we've ever had. If there are structures larger than the Hercules-Corona Borealis Great Wall, the 2030s are when we'll find them. But even with those tools, there's a limit. The observable universe has an edge, set by the cosmic microwave background. Beyond that edge, we can't see using light because there was no free-travelling light before the universe became transparent. If a structure exists entirely beyond that edge, or if it straddles the boundary in a way that makes most of it invisible, we'll never detect it directly. We can only infer it from its gravitational effects on the things we can see, and those inferences get weaker the farther out you go. So the search for larger structures is not just about building bigger telescopes, it's about figuring out how to extract information from data that are sparse, noisy, and incomplete. It's about developing statistical tools that can distinguish real patterns from projection effects and random fluctuations. It's about running simulations that test whether the structures we're seeing are consistent with the standard model or whether they require new physics. And that brings us to the second big question. If the Hercules-Corona Borealis Great Wall is real, if it really does violate the cosmological principle, what kind of new physics would explain it? What could make a structure that large? There are a few ideas, and none of them are comfortable. The first is that the initial conditions in the early universe were lumpier than we thought. The cosmic microwave background shows tiny temperature variations, about 1 part in 100,000, but those variations are averaged over large regions of the sky. If there were rare, large amplitude fluctuations that don't show up clearly in the CMB but were there nonetheless, gravity could have amplified them over time, building structures larger than the standard predictions allow. This idea isn't crazy, but it requires tweaking the inflation models in ways that are hard to justify without independent evidence. Inflation, the theory that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang, predicts a specific pattern of fluctuations. If you change that pattern to allow for larger structures, you risk breaking the other things inflation gets right, like the smoothness of the CMB and the flatness of space. The second idea is that gravity behaves differently at very large scales. General relativity, the theory that describes gravity as the curvature of space-time, has been tested extensively at scales ranging from the solar system to galaxy clusters. It works everywhere we've checked, but we've never directly tested it at scales of billions of light years. It's possible that general relativity breaks down or gets modified at those distances, allowing structures to grow larger than the standard predictions. Modified gravity theories exist, and some of them predict stronger clustering at large scales. But most of those theories have problems. They struggle to match other observations like the rotation curves of galaxies or the bending of light by galaxy clusters. You fix one problem and create 3 others. A third possibility is that the expansion history of the universe was different. The lambda CDM model, the standard model of cosmology, assumes that the universe has been expanding at a rate determined by the amounts of matter, and dark energy. Dark energy, the mysterious force driving the accelerated expansion, is assumed to be constant over time, a cosmological constant in Einstein's equations. But what if dark energy wasn't constant? What if it was stronger or weaker in the early universe? A different expansion history would change the timescales for structure formation. Maybe gravity had more time to build large structures because the expansion was slower at certain epochs. Or maybe the expansion was faster, which sounds counterintuitive but could affect the way matter clumped in subtle ways. Testing this idea requires precise measurements of the expansion rate at different times in the universe's history. Astronomers are working on this using supernovae, quasars, and other distance indicators. So far, the data are consistent with a constant dark energy, but there are hints of tension. The Hubble constant, the current expansion rate, seems to depend on how you measure it. Some methods give a higher value, others a lower value. That tension might be a clue that something in the expansion history isn't quite right. Or it might just be a measurement problem that will go away with better data. Nobody knows yet. A fourth possibility, and the one many astronomers favour, is that the Hercules-Corona Borealis Great Wall isn't actually a single coherent structure. It might be a projection effect, a chance alignment of several unrelated overdensities that happen to lie along the same line of sight from Earth. If that's the case, there's no new physics required. It's just geometry, perspective, the universe playing tricks on our line of sight, proving that requires more data. You need to map the region in detail, measure the distances to individual galaxies, and see whether the overdensities are actually connected by a filament, or just happen to appear near each other on the sky. That work is ongoing. Future surveys with better instruments and larger samples of galaxies will help settle the question. So the search for new physics is tied directly to the question of whether the Great Wall is real. If it's not real, the standard model survives intact, and we move on. If it is real, something in the standard model is incomplete, and we're forced to figure out what's missing. Either way, the answer matters, because cosmology is not just about cataloguing structures, it's about testing the models. Every observation is a test. Every structure we find is a constraint on what the universe can do, and when we find something that doesn't fit, it's an opportunity to learn something new. Now let's talk about the tools. Because the future of cosmology isn't just about ideas, it's about instruments, telescopes, satellites, surveys. The ability to collect more data, better data, data that can answer questions we couldn't even ask a decade ago. The James Webb Space Telescope, launched in December 2021, is already changing the game. Webb is an infrared telescope designed to see through dust and detect the stretched light from the most distant galaxies. Its primary mirror is 6.5 meters across, more than twice the diameter of Hubble's, and its instruments are sensitive to wavelengths that Hubble couldn't reach. Webb can see galaxies as they were less than 500 million years after the Big Bang, a time when the universe was still assembling its first structures, and what it's finding is surprising. Galaxies at those distances are brighter and more massive than the models predicted. Some of them look like they've already gone through multiple generations of star formation, building up heavy elements and assembling into organised structures on timescales that seem too short. That's not a crisis yet, but it's a tension. The same kind of tension we've been talking about with the Hercules-Corona Borealis Great Wall. The observations are pushing up against the limits of what the models allow. Euclid, the European Space Agency's dark energy mission, is designed to map the three-dimensional distribution of galaxies across more than a third of the sky. Its goal is to measure the expansion history of the universe with unprecedented precision, tracing how dark energy has affected the growth of structure over billions of years. Euclid surveys will cover billions of galaxies, mapping their positions and distances, and the resulting data will give us the most detailed picture of the cosmic web ever assembled. If there are large-scale structures hiding in the data, structures like the Great Wall or even larger, Euclid will find them. Its first data releases are expected in the mid-2020s, and the full survey will take about 6 years to complete. The Nancy Grace Roman Space Telescope, named after NASA's first chief astronomer, will have a field of view 100 times larger than Webb's. That wide field makes it ideal for large area surveys, the kind that can map huge swaths of the sky and detect patterns that aren't visible when you're looking at one small region at a time. Roman is designed to study dark energy, but its surveys will also map large-scale structure, detect distant supernovae, and measure the properties of galaxies across billions of years of cosmic history. Launch is currently scheduled for the mid-2020s, and once it's operational, Roman will work in tandem with Webb and Euclid, each telescope covering a different piece of the puzzle. Together, those three instruments are going to push the map farther than it's ever been. They'll detect fainter galaxies, measure more precise distances, and reveal structures that are currently too distant or too faint to show up in existing surveys. The 2030s are going to be a golden age for observational cosmology. Not because we'll suddenly understand everything, but because we'll have the data to ask much harder questions. And beyond those three, there are ground-based surveys like the Vera C. Rubin Observatory, which will conduct the legacy survey of space and time starting in the mid-2020s. Rubin will image the entire southern sky every few nights, creating a time-lapse movie of the universe that will capture everything from nearby asteroids to distant supernovae. Its dataset will be enormous, on the order of tens of petabytes, and analysing it will require new computational tools, machine learning algorithms, and collaboration across the entire astronomical community. Then there's the next generation of radio telescopes. The Square Kilometre Array, or SKA, is a planned radio observatory with a collecting area of 1 square kilometre, spread across thousands of individual antennas in Australia and South Africa. SKA will be the most sensitive radio telescope ever built, capable of detecting hydrogen gas in galaxies halfway across the observable universe. Hydrogen is the most common element in the cosmos, and mapping its distribution gives you a different view of large-scale structure than you get from optical or infrared surveys. SKA will trace the cosmic web in ways that are complementary to what Webb, Euclid and Roman can do, filling in gaps and revealing structures that don't show up clearly in other wavelengths. All of these instruments are being built or planned right now. Some are already operational, others will come online in the next few years, and together they're going to produce more data than astronomers have ever had to work with. That's exciting, but it's also overwhelming, because data by itself doesn't answer questions. You have to analyze it, model it, test hypotheses, rule out alternatives, and figure out what the patterns mean. That takes time, it takes collaboration, it takes new statistical methods and new computational tools. The limiting factor in cosmology over the next few decades won't be the amount of data, it'll be the ability to make sense of it. But assuming we can make sense of it, assuming the surveys work and the instruments perform as designed, what will we learn? What questions will be answered, and what new questions will emerge? One of the biggest open questions is the nature of dark energy. We know it exists because the expansion of the universe is accelerating. We know it makes up about 70% of the universe's total energy budget, but we have no idea what it is. The simplest explanation is that it's a cosmological constant, a property of space-time itself that doesn't change over time. But that explanation has problems. The value of the cosmological constant, if you try to calculate it from first principles using quantum field theory, comes out wrong by a factor of 10 to the power of 120. That's not a small error. That's the worst prediction in the history of physics. Something is deeply wrong with our understanding of either dark energy or quantum mechanics or both. Euclid and Roman are designed to measure dark energy's properties with enough precision to tell whether it's really constant or whether it's changing over time. If it's changing, that opens the door to a whole new set of models. Maybe dark energy is a field, like the Higgs field, that evolves as the universe expands. Maybe it's a consequence of modifications to general relativity at very large scales. Maybe it's something we haven't thought of yet. The data from the 2030s will constrain the possibilities, and whatever we find, it's going to reshape our understanding of how the universe works. Another open question is the ultimate fate of the universe. Where is all this going? What happens in the far future, trillions of years from now, when the stars have burned out and the galaxies have drifted beyond each other's horizons? The answer depends on dark energy and the overall density of the universe. If dark energy remains constant and the expansion keeps accelerating, the universe will keep getting larger, colder, and emptier forever. Stars will exhaust their fuel. Galaxies will fade. Eventually, even black holes will evaporate through Hawking radiation, a process that takes 10 to the power of 100 years. After that, the universe will be a cold, dark, dilute soup of particles that almost never interact. Physicists call this the heat death, or the big freeze. It's the most likely outcome based on current observations, but there are alternatives. If dark energy is not constant, if it weakens over time, the expansion might slow down, and if it reverses, if gravity eventually wins and starts pulling everything back together, the universe could recollapse into a big crunch. The timescale for that would be tens of billions of years at minimum, possibly much longer. The Big Crunch was the favoured scenario for a while in the mid-20th century, back when astronomers thought the universe might be dense enough for gravity to halt the expansion. Then in the late 1990s, observations of distant supernovae revealed that the expansion is accelerating, not slowing, and the Big Crunch fell out of favour. But it's not impossible. If dark energy behaves in ways we don't currently understand, if it can change sign or decay into something else, the universe's fate is still open. There's a third option, stranger, and less discussed. If dark energy continues to grow stronger over time, the acceleration could become so extreme that it eventually tears apart not just galaxies and stars, but atoms themselves. This is called the Big Rip, and it would happen if dark energy were what physicists call phantom energy, a type of field with a very specific property that causes it to increase as the universe expands. In the Big Rip scenario, the universe doesn't end in cold emptiness or a fiery collapse. It ends in disintegration. Space itself expands so fast that the distances between particles grow faster than the forces holding them together can compensate. First galaxies are torn apart, then stars, then planets, then molecules, then atoms, then atomic nuclei. Eventually, even space-time itself might fragment. The timescale for this would be on the order of tens of billions of years, assuming the current estimates of dark energy's properties are even close to correct. Most physicists think the Big Rip is unlikely, but it's allowed by the equations, and that alone is unsettling, so the ultimate fate of the universe is not settled. It depends on measurements we haven't made yet, observations that will come from instruments currently being built. The data from Euclid and Roman will help narrow the possibilities, but there's a limit to how precise those measurements can be, and there's always the possibility that dark energy will surprise us, that it will behave in ways none of the current models predict, and if that happens, the endgame changes. Here's the uncomfortable truth. Cosmology is full of limits, not just observational limits like the edge of the observable universe, but fundamental limits set by the structure of reality itself. Some questions might not have answers, not because we're not smart enough, but because the information needed to answer them doesn't exist or can't be accessed. Take the question of what lies beyond the observable universe. We can speculate. We can build models. We can argue about whether the universe is infinite or finite, whether it loops back on itself, whether the laws of physics are the same everywhere. But we can't observe it. By definition, the unobservable universe is unobservable, and if we can't observe it, we can't test hypotheses about it, which means those hypotheses aren't science in the usual sense. They're philosophy, or mathematics, or informed guesses. Interesting, maybe even correct, but not provable. Or take the question of what happened before the Big Bang. The phrase itself might not make sense. If time itself began with the Big Bang, then asking what came before is like asking what's north of the North Pole. The question assumes a framework that doesn't apply. Some models, like eternal inflation, suggest that our Big Bang was just one event in a much larger multiverse where Big Bangs happen all the time, but those models are speculative and maybe untestable. Other models suggest that the universe goes through cycles, expanding and contracting. Big Bang followed by Big Crunch followed by another Big Bang over and over. But testing that requires information from before the last Big Bang, and that information, if it ever existed, was likely erased by the singularity. So there are questions that might be permanently out of reach. And that's hard to accept. Because humans are pattern-finding, question-asking, boundary-pushing creatures. We don't like unanswered questions. We don't like mysteries that can't be solved. We want the map to be complete. But the map, by its nature, always has edges, and some of those edges are set by the universe itself, not by the limits of our tools. But here's the thing. Even when we reach a limit, even when we hit a boundary that can't be crossed, the act of reaching it teaches us something. Because limits tell you about the structure of the problem. They tell you what's possible and what's not. They force you to refine your models, sharpen your questions, and think more carefully about what you're actually trying to learn. The edge of the map is not a failure. It's a success. It means you've gone as far as you can, and now you know where the boundary is. And sometimes, when you think you've hit a limit, someone finds a way around it. A new technique, a new instrument, a clever piece of reasoning that opens a door you didn't know was there. The cosmic microwave background was thought to be the earliest light we could ever see, the absolute limit of observation. Then physicists realized that neutrinos and gravitational waves, which interact so weakly with matter that they pass through the opaque early universe without scattering, could in principle carry information from even earlier times. We haven't detected primordial neutrinos or gravitational waves from the Big Bang yet, but we're building detectors that might. If we succeed, the boundary shifts. What looked like a limit becomes a stepping stone. That's the history of cosmology. Every limit that looked permanent turned out to be provisional. The Milky Way was the universe until we realized it wasn't. The observable universe was static until we discovered it's expanding. The expansion was thought to be slowing until we found out it's accelerating. Every time we thought we'd reached the edge moved. And the new view revealed more questions, more mysteries, more structure than anyone expected. So what lies next? More surprises, more tension between observation and theory, more structures at the edge of what the models allow, more evidence that the universe is stranger, more complex, and more interesting than we thought. The Hercules-Corona Borealis Great Wall, real or not, is a preview. It's a reminder that the map is not finished, that the boundaries are not fixed, that the universe still has secrets we haven't uncovered. The 2030s will bring new data, new surveys, new instruments. Those tools will answer some questions and raise others. We'll map larger volumes of space, detect fainter galaxies, measure dark energy's properties with greater precision. We'll find new structures, some of them probably larger than anything we've seen before. We'll test the cosmological principle more rigorously. And somewhere in all that data, there will be anomalies, things that don't fit, observations that challenge the models, because that's how science works. The map grows, the models improve, but the fit is never perfect. There are always outliers, always gaps, always places where the data and the theory don't quite line up. And those gaps are not problems, they're opportunities, because science doesn't progress by confirming what we already know. It progresses by finding things that don't fit and figuring out why. Every major breakthrough in cosmology, from the discovery that the universe is expanding to the realization that most of it is made of dark matter and dark energy, started with an observation that didn't match the predictions. Someone saw something they weren't supposed to see, and instead of ignoring it or dismissing it as error, they took it seriously. They asked why. They tested it. And eventually the anomaly became the foundation for a new understanding. The Hercules-Corona Borealis Great Wall might be that kind of anomaly, or it might be a projection effect that disappears with better data. Either way, the process is the same. Observe, measure, test, refine. Push the map farther, ask harder questions. And when you hit a limit, figure out whether it's a real boundary or just the edge of what you can currently see. That's the enduring mystery, not the specific question of whether the Great Wall is real, but the larger question of what the universe is and how it works. We've come a long way in the past century. We've gone from thinking the Milky Way was the entire cosmos to mapping structures 10 billion light years across. We've traced the history of the universe from the Big Bang to the present. We've figured out that most of the universe is invisible, made of dark matter and dark energy that we can measure but not directly detect. We've built models that explain the formation of galaxies, the growth of structure, the accelerated expansion, and those models work. They make predictions that match the observations, at least most of the time, but they're not complete. There are gaps, tensions, anomalies. The Hubble constant depends on how you measure it. The largest structures seem bigger than they should be. The earliest galaxies found by Webb look too mature for their age. Dark energy is a placeholder, a name for something we don't understand. Dark matter is the same. We know they're there because we can see their effects, but we have no idea what they actually are. The models describe how the universe behaves, but they don't explain why. They don't tell us what dark energy is, or why the cosmological constant has the value it does, or whether the laws of physics are the same everywhere, or what came before the Big Bang. Those are big questions. Some of them might have answers, some of them might not. But the act of asking is what drives cosmology forward. Because even when the questions are too hard, even when the answers are out of reach, the process of trying teaches us something. About the universe, yes, but also about ourselves, about what it means to be a species that looks at the night sky and wonders how far it goes, a species that builds instruments to measure things it will never touch, a species that spends lifetimes trying to understand a cosmos that, by every measure, is indifferent to whether it's understood or not. And that indifference is not a reason to stop, it's a reason to keep going, because the universe doesn't care, but we do. And that caring, that curiosity, that refusal to accept mystery as the final answer is what makes us human. It's what separates us from rocks and gas clouds and the vast stretches of empty space between the stars. We're the part of the universe that woke up and started asking questions, and the questions don't stop just because the answers are hard. So what lies next? The same thing that's always come next. Another edge, another boundary, another mystery waiting at the limit of what we can see. The Hercules-Corona Borealis Great Wall, 10 billion light years long, sitting at the edge of the observable universe, is a signpost. It says, here is where the map currently ends. Here is what we've found so far, and here, just past the horizon, is everything we haven't found yet. The map will keep growing, the tools will keep improving, the questions will keep getting harder. And somewhere in the data, in the noise and the patterns and the outliers that don't quite fit, there will be another surprise, another structure, another challenge to the models, another reminder that the universe is larger, stranger, and more complex than we thought. That's the continuous journey, not toward a final answer, because there probably isn't one, but toward better questions, deeper understanding, a map that covers more territory, even as the territory itself keeps revealing new edges. We're standing at one of those edges right now, staring at a structure that might be real and might not, a feature so large it pushes up against the limits of what the models allow. And whether it holds up under scrutiny or fades into statistical noise, the process of investigating it, of testing the boundary, of asking whether the rules we've been using are complete, is the point. Because the universe is not done surprising us. The map is not finished. And as long as there are questions we can't answer, as long as there are mysteries waiting at the edge of what we can see, cosmology will keep moving forward, building better instruments, running deeper surveys, asking why. That drive, that refusal to stop at the edge, is what got us from believing the Earth was the center of everything to measuring structures 10 billion light-years across. And it's what will carry us forward into whatever comes next. The story doesn't end here. It never does. Every answer opens new questions, every discovery reveals new mysteries, and every time we think we've mapped as far as we can go, someone finds a way to push a little farther. That's the nature of exploration. That's the nature of science. And that's the nature of being human in a universe so much larger than us that it makes the word large feel like an insult. So we keep looking, keep measuring, keep asking, not because we'll ever finish the map, but because the act of drawing it, the process of pushing the boundary one more step, is the only thing that makes the vastness bearable. We're small, we're temporary, we're cosmically insignificant. But we're here, and we're curious. And that curiosity, however brief, however local, however irrelevant it is at the scale of 10 billion light-years, is enough. The edge is not the end. It's an invitation, a challenge, a question written in starlight and stretched across the void. What's next? What's beyond? What have we not seen yet? The universe isn't going to answer, but we're going to keep asking anyway. Because that's what we do. That's who we are. And as long as there's an edge, as long as there's something beyond it we haven't mapped yet, the journey continues. So here we are, standing at the edge of what might be the largest structure in the universe, 10 billion light-years, a filament of galaxies stretching across nearly 11% of everything we can see. The Hercules-Corona Borealis Great Wall. Real or not, confirmed or contested, it's become something more than a data point. It's become a boundary, a test. A question written in gamma-ray bursts and distant galaxies that forces us to ask whether the rules we've been using are actually complete. We started with black holes, the densest objects in existence, points where space-time folds in on itself and nothing escapes. Then we zoomed out to galaxies, islands of hundreds of billions of stars held together by gravity and dark matter. Then superclusters. Laniakea, our cosmic home, 520 million light-years across, containing 100,000 galaxies flowing toward a common center. We traced the cosmic web, the filaments, and voids that organize matter across the larger scales. And we pushed all the way to the edge of the observable universe, the boundary set by light and time, beyond which we cannot see and never will. Every step of that journey made us smaller, and every step revealed something larger than we expected. The universe keeps doing that, keeps showing us that the map is incomplete, that the territory extends farther than the models predict, that the things we thought were limits were just the edge of what we could see at the time. The Great Wall sits at that edge. Not because it's the farthest thing we've detected, though it's close, but because it represents the boundary between what fits and what doesn't, between confirmation and crisis. If it's real, something in the cosmological principle is incomplete. If it's not, it's a reminder that sparse data and pattern recognition can fool us into seeing structure where there's only noise. Either way, the question remains. What else is out there? What structures are we missing because they're too faint, too distant, or oriented in ways that make them invisible to our current tools? The universe is under no obligation to fit inside our models, and the more we look, the more we find things that don't quite fit. That's not failure, that's the process. You're one arrangement of atoms on one planet in one galaxy among 2 trillion. The light reaching your eyes right now from distant stars left those stars years, decades, centuries ago. You're seeing the past, always the past. The present is invisible at cosmic scales, and the things you're looking at, the galaxies and clusters and walls stretched across billions of light years, they don't know you're watching.